إذا قومك منه يصدون وقالوا أآلهتنا خير أم هو ما ضربوه لك إلا جدلا بل هم قوم خصمون.
Good morning. Let me know if I'm audible. Good morning. Let me know if I'm audible. Let us start today's class then. Is volume fine now? Okay. Chali, let us start the subject then. Yesterday we have discussed the concept of buoyancy, and then we have also discussed the concept of what we call rigid body motion. So let me write today's date first. Okay. So yesterday we have discussed buoyancy and we have discussed rigid body motion also. I gave you a question yesterday as a homework question, but I have myself done a mistake in that question. Once, let me go back to that particular slide. I think this was a slide where I have done a mistake. If you check over here, I have mentioned this correctly, but coming to this particular step, I have forgotten to write 64. I just wrote 4 over here. Since I wrote 4 over here, everything from here onwards was having an error. Therefore, my answer in the next slide also is wrong. Okay, the answer over here is wrong. So I hope you have corrected the mistake. I hope you could correct the mistake over there. And of course, the spirit of the solution remains the same. Only thing is there is a mistake from here onwards. Okay. I think the answer should be somewhere in 30s. The value of theta will be somewhere in 30s. Someone had sent me the answer also yesterday. Can anyone tell me the answer? What exactly should be coming? Yes, what is the value of theta you are supposed to get? The pattern of solutions will remain the same. Only thing, the value changes. Yes, anyone getting the correct answer? No, 76.52 I don't think is the answer. Any other answer? I hope you're following. The mistake I have done is I just took, instead of 64, I took 4 over here. Okay, probably 34.57. If you have not done, the pattern of solution still remains the same. Okay, you check the answer today at least. Try doing it today at least. You should be getting somewhere near 34, 35 probably. Actually, let us get back to our subject today. Today I'm going to do some problems from the previous chapter, that is statics, entire statics chapter. I'll be doing some problems now. Let us start problems today. Look over here. Let us start with question 1 for today's class. Question 1. Imagine you are having a container. Suppose you have some container over here. There is some container, let us say. In this container, you are having a fluid filled. There is some fluid filled over here. There is some fluid filled over here. Okay, some fluid is filled over here. Let us say the height over here is equal to this height over here is equal to some 3 meters. This height over here is equal to 3 meters. And this height over here is equal to, let us say, some 2 meters. The height over here is 2 meters. This width over here is equal to 8 meters. Width over here is 8 meters. Let us say I'm accelerating this entire container with some acceleration AX. The question over here is, what is the maximum value of AX? What is the maximum value of AX for which the fluid does not spill out of the container, out of the container. What is the maximum value of AX you can attain for which the fluid does not spill out of the container? You can take the value of G as 10 meters per second square. And don't use a calculator for this question. Chaliye, please start the question now. Start the question. Don't use calculator for this question. This is very simple. Yes, I'm waiting for your answers. Very good, Yash. Perfect answer. Yes. Chaliye. How to answer this question? This is very simple. Imagine the solution now. One second. Imagine the solution now. Let us say the container is having some position like this. You'll be having the fluid in this position. In this position, let us say the fluid comes in this particular position. It is just about to spill out. When it is just about to spill out, that time, let us say the horizontal level, which previously was a level, is something like this. Okay. So this angle over here is angle theta. We know that this height is equal to how much? 2 meters. And we know that this distance, when it is just about to spill out, this distance is exactly half the distance. That is, from here, it is going to have some kind of inclination. So this is half of 8 meters, that is equal to 4 meters. I see from here that the value of theta has to be equal to tan inverse of opposite over here is 2, adjacent over here is 4. Tan inverse of 2 by 4, which should also be equal to tan inverse of, we know the formula, AX upon G. Yesterday we have mentioned this formula, AX upon G. So now you can equate both these things. What do you get? Half is equal to AX upon G. G over here is 10, which implies the value of AX over here happens to be equal to 5 meters per second square. I hope the question was simple for you. This is very simple question only. So AX over here is supposed to be equal to 5 meters per second square. Now, in this question itself, find out the value of acceleration at which, the minimum value of acceleration at which the hydrostatic force on the front wall, let us say this is front wall, and this is rear wall. Okay, so let me do one thing. Let me first of all create a duplicate slide for this. Let us say now the question over here is, one second. Question 2 over here, let us say. Question 2 over here. Minimum AX when hydrostatic force on front wall is 0. Minimum AX when hydrostatic force on front wall happens to become 0. Actually, find this out. Minimum value of AX such that hydrostatic force on the front wall becomes equal to 0. Find this out. What is the minimum value of AX when hydrostatic force on the front wall becomes equal to 0? Yes, I have two questions, extra questions given over here. Question number 2 and question number 3. Please try. Perfect answer. Amit Anil Shawan. Perfect answer. Try question number 3 also. Yes, Venkat Ramna, correct answer. Now, when will the value of hydrostatic force on the front wall become equal to 0? For hydrostatic force on the front wall to become 0, the fluid should have no contact whatsoever with the front wall. The fluid should leave contact with the front wall. That means you are going to have the interface starting from here, and coming up till here. The interface starting from here, coming up till here. So let us say this is how much fluid you are going to have. This is how much fluid you are going to have. And this portion, let us say, is going to become 0 portion. So this is how much fluid you're going to have. Now ask yourself that the value of theta, let us say in this particular case, the value of theta would be equal to how much? I'm solving for question number 2 over here now. Solution for question number 2. Okay, solution for question number 2. Yes, the value of theta is supposed to be equal to how much? Theta is supposed to be equal to tan inverse of, look at this triangle over here. What is the opposite over here? 5. What is the adjacent over here? 8. Should also be equal to tan inverse of, what do you have over here? AX upon G. You compare 5 by 8 to AX upon G, then what are you going to get? 50 by 8 is equal to AX. From there you will get the value of AX to be equal to 6.25 meters per second square. Please check this thing. You are going to get the value as 6.5 meters per second square. 6.5 meters per second square. Okay. So the minimum value of AX for which hydrostatic force on the front wall is 0 will be 6.25 meters per second square. Third question is very simple. It is an aptitude based question. What percentage of fluid is spilled out? This is percentage, okay? It might not be clear. This is actually percentage. What percentage of fluid is spilled out for the condition in question number 2? Okay. How much fluid is being spilled out? Let us say solution for question number 3 now. Solution for question number 3. These are very simple questions. Okay. How to find this out? Initial volume. Ask yourself how much is initial volume? Initial volume is equal to how much? Look over here. Initial volume from here you can say is the cross section multiplied to width. The cross section over here is equal to how much? You see 3 by 8. So it is equal to 3 by 8 multiplied to width. That is equal to 24 W. Final volume is equal to how much? What is the final volume in this particular case? Final volume. This cross section. What is this cross section? Half base height. Half base height means half into base is 8. Height is equal to 5. Into width. This is equal to 20 W is the final volume. So how much volume is lost or spilled volume is equal to how much? Come on, this is very simple. Spilled volume has to be equal to how much? Initial volume minus final volume. That is equal to 4 times W is a spilled volume. Okay. So percentage lost. I don't have sufficient space over here. I hope you can adjust. Percentage spilled is equal to how much? 4W divided by initial is equal to 24W multiplied to 100%. Now what value will this be equal to? This comes out to be 1/6 of 100%, that is equal to 16.67%. 16.67% is the answer. Very good. Many of you have given correct answer also. So the answer over here is 16.67%. Now you're seeing that in the subject of statics, there is a lot of importance for aptitude involved. Okay, lot of importance for aptitude is involved over here. That is why I am repeating this again. Please practice aptitude based questions daily for 15-20 minutes. That will only help you. There is no disadvantage of spending some time on aptitude. Only thing is spend wisely. Okay, don't over involve yourself. 15-20 minutes is sufficient, not more than that. Take it. Now let us go for the second topic. We have taken a question on the concept of rigid body motion. Let us now go further. I have seen that many of you have asked me questions regarding, one second, if anyone wants to take a snapshot, you can take very quickly. I have seen that many of you have asked questions regarding hydrostatics on flat plates. You are having some difficulty in solving some questions based on equilibrium. Okay. For that purpose, I'm going to take a question from GATE examination. Okay. From GATE examination, I'm going to take a particular question. The question goes something like this. Look at this question. Very interesting, very good question. This is GATE 2013 2-mark question. GATE 2013 2-mark question. It is based on hydrostatics on flat plate. Very, very good question. One of my favorite questions from this topic. Okay. The question says that suppose you are having a horizontal level, something like this. Let us say this is perfectly hot. See, my horizontals are slightly inclined. So you adjust these. Let us say you're having some horizontal level, horizontal ground is there. Fine. And somewhere over here, you are having a hinge. You are having a hinge somewhere over here. Then from this hinge, you are having a gate. This over here is a gate. Let me name this gate as some gate OA. Let me name this gate as some gate OA. Fine. You're having some gate over here. Then let us say you're having some fluid on top. This is water, let us say, for example. You're having water on top over here. You're having water on top. This over here is water. So let me mention This is water. Interface over here. This is a gate. Let me again mention over here. OA is a gate. The length of this gate OA is equal to 5 meters. Length of the gate OA is equal to 5 meters. This bottom surface is a ground surface. Also mentioned to you that this angle over here is equal to 30 degrees. This angle is equal to 30 degrees. Okay. The question asked is, what is the minimum mass per unit width required for gate OA, comma, such that it doesn't open. The gate doesn't open. What is the minimum mass per unit width required for gate OA such that it is not opening up? Okay, this is the question we are having. Now, read this question, take a moment and plan how to approach this question. Take a moment and plan how to approach this question. Chali. I hope you have all thought over it, how to approach this particular question. Now look over here. Imagine that this over here is a gate. This is a gate we are having. Okay. Right now, what is happening on this gate is, let me create duplicate slide so that you can understand this better. This is a duplicate slide I'm having. Okay. Previous slide is over here. This is a duplicate slide. Now, right now, what is happening is, on this particular gate, the hydrostatic force is applying some kind of thrust like this. This is a hydrostatic force we are having. Hydrostatic force. Now, the moment we are having this hydrostatic force, what is happening due to hydrostatic force now? This particular gate is going to experience some kind of movement in this particular direction. That is, an anti-clockwise movement is developed about hinge O, so that this gate is trying to open up. You see, the fluid is pushing, and since the fluid is pushing, anti-clockwise movement is developed over here. Now, you don't want the gate to open up. If you don't want the gate to open up, you should apply some resisting moment. For example, there are some options I have. One option I'm having is, let us say, I apply some force over here. I apply some resisting force. Okay, this resisting force will create a counter moment. If both of them balance each other, fine, everything is fine. That is one option I'm having. Second option, instead of applying resisting moment, let us say, instead of applying resisting force, I'm straight away applying a resisting moment. Okay, at point O itself, you can create some resisting moment also. That is one more option. But over here, third option is given. What is the third option given over here? You are not applying any kind of force for resistance. You are not applying any kind of moment for resistance. The self weight of this particular gate is taking care. So imagine that this is a gate you are having. This gate is having some self weight over here. Example, it is having some self weight over here. This self weight about point O is going to create a resisting moment. That is a question asked over here. What should be the minimum mass? Because you see, weight is by the virtue of mass. If you don't have mass, you can't have weight. The question is saying, what is the value of minimum mass? Kam se kam kitna chahiye? Minimum, how much is required per unit width? That means this gate is supposed to have some width perpendicular to your screen. That width is equal to 1 unit. So per unit width, how much minimum mass of the gate is required so that the system is right now is in equilibrium? I hope you are able to follow the question over here. Okay. Chali. Let us now start how to solve this question. This question is purely based on this question. One second, please. This question is purely based on mechanics. Okay. This question is purely based on mechanics. So I have to establish equilibrium. For establishing equilibrium, I'm going to start with the concept of free body diagram first of all. So let me write over here, solution. Solution. I'm going to start with the concept of free body diagram. I'm starting the concept of free body diagram of this gate OA. Let us say the gate OA is something like this. This is the gate OA we are having. Let us say this point over here is certain point O. This point over here is certain point A. Okay. I have to now show all the forces acting on this gate OA along with the distances and directions. First thing, I know that point O is having a hinge, therefore it is supposed to have some hinge reactions. Let us say these are the hinge reactions. Horizontal at O, vertical at O, hinge reactions I'm having. Don't worry about the hinge reactions direction. If they are wrong, the answer will correct itself. Don't worry. Next thing, I know that there is going to be a certain point over here, which is known as center of pressure. A certain point, let us say, known as center of pressure. Let us say this is center of pressure. On center of pressure, you are supposed to have a hydrostatic force concentrated. There is supposed to be certain hydrostatic force concentrated on center of pressure. And mind you, this hydrostatic force is supposed to be perpendicular to plate. We have discussed this thing also. Hydrostatic force, gamma area H bar, is always supposed to be perpendicular. Taking further, one more force we are having. That force is going to act exactly at the centroid or center of gravity of the plate. That force over here is the weight of this particular plate. Let me represent by W, which is basically equal to mg. mg. This point at which you are going to have your weight concentrated. Apart from this, there is going to be one more force. What force is that? You see this point A over here. Imagine the gate is just resting at this particular surface, horizontal surface. This is horizontal surface. The gate is resting over this horizontal surface like this. The moment there is a contact, there has to be a contact reaction force in the name of normal. So there's supposed to be some normal. There is supposed to be some normal over here. But there's a problem. The problem is the question over here is asking minimum mass. Minimum mass means at this particular mass, the gate is just about to open up. If the gate is just about to open up, imagine KJ please, okay, the fluid force is sufficient for the gate to just open up, okay, just open up. If it is just about to open up, that means the contact is just about to get lost. If the contact is just about to get lost, the normal is supposed to be equal to how much? 0. Please understand this thing. Normal over here is equal to 0 since the gate is just losing contact, just losing contact. Why is it just losing contact? Since minimum mass is mentioned. Minimum mass is mentioned. Since you're having minimum mass, so as to maintain equilibrium. I hope you are following all these things. Now next thing, angle we know over here. We know this angle over here is equal to 30 degrees. Distances are required. You see, I am having forces over here which are non-concurrent. My logic always is whenever you have non-concurrent forces, always think of moment equation. And moment should be always taken about such a point about which maximum number of unknowns are not contributing. For example, if I take moment about this particular point O, then HO and VO, which are the reactions at point O, which are unknowns, they won't contribute in that moment. So my idea is take distances from point O. I am going to take the distances measured from point O. Now you have to answer me this thing quickly. Tell me quickly, how much is the distance from O to G going to be equal to? How much is the distance from O to G going to be equal to? Yes, please. Very good. It is going to be equal to 2.5 meters. Perfect. This distance will be equal to, this distance over here will be equal to 2.5 meters. Next, answer me this thing. How much is the distance? Now, this is very important. How much is the distance from O to P equal to? The distance from O to P equal to. If you are not able to answer this distance, the question becomes very lengthy for you. Yes, please. O to P, how much is the distance? O to P. Very good, very good. This is really encouraging for me. Many of you have given answer, correct answer. Jayavardhani, answer is wrong. Okay. Smita Gaikwad, answer is wrong. The answer over here is supposed to be, think logically now. What is the logic over here? Let me create a duplicate file, duplicate frame. Think logically over here. You're going to have some kind of triangular kind of loading. Triangular kind of loading. So you're having this kind of triangular loading over here. If you have triangular loading on this particular gate, we know that the force is going to get concentrated at what distance? This is something like a strength of materials now. You know, for a triangular loading, 2/3 from here or 1/3 from the bottom. So 2/3 from here means what? 2/3 from top basically means, I'm coming back to the original slide, 2/3 of 5. 2/3 of 5 meters, that is equal to 3.33 meters is what you're going to get. This distance is 3.33 meters. Very quickly take down the free body diagram. Okay, draw the free body diagram quickly, please. I hope all of you are following why I'm getting 2/3 over here. The logic behind 2/3 is, look at the next frame. You are having a triangular loading you're having over here. For triangular loading, we know that you are going to have from the vertex 2/3 distance. From the base, you are going to have 1/3 distance. That is the logic I'm using. Okay. Please be quick. After having drawn the free body diagram, now I'm going to write the equation of moment. The equation of moment is summation of moment about point O has to be equal to how much? 0. The net moment about point O has to be equal to 0. What do I mean by net moment about point O equal to 0? I see that n is not contributing towards the moment whatsoever because the value of n is equal to 0. I have only two forces contributing towards the moment. One force is W, the other force is F. So I can say this implies that the magnitude of moment of W about point O has to be equal to the magnitude of moment of force F about point O. Okay. Why am I equating the magnitudes? Because they are creating counter moments to each other. F is creating anti-clockwise, W is creating clockwise moment about O. Okay. This implies W multiplied to its lever arm. Think logically now. How much is the lever arm going to be? Just think that I'm completing this particular diagram. If I complete this particular diagram, you can say that this angle over here has to be equal to how much? It has to be equal to 30 degrees. The lever arm over here is from here till here. Look at my cursor, please. Look at my cursor. The lever arm is going to start from this point up till this particular point. What is this lever arm over here equal to? This lever arm is 2.5 cos 30. W multiplied to 2.5 cos 30 degrees has to be equal to F multiplied to what is the lever arm over here? Since he is himself perpendicular to the gate, I can say the lever arm over here is 2 times 5 by 3, that is equal to 10 by 3. 10 by 3. Which further implies W basically means mass times acceleration due to gravity multiplied to 2.5 cos 30 has to be equal to gamma into area into h bar multiplied to 10 divided by 3. Multiplied to 10 divided by 3. This is the value you are going to get. Okay. Now, I want you to observe G I'm having over here and G I'm having in gamma also. Let us say I cancel G on either side. I'll be left with density. I'll be left with density. Area of the plate. Quickly tell me how much would the area of the plate be equal to? Remember, you are having a unit width perpendicular to the surface. So the area of the plate, look at my cursor now. Area of the plate over here is 5 multiplied to the width. So area over here will be equal to only 5. H bar will be equal to how much? What will the value of H bar over here be equal to? The value of H bar will be equal to, look carefully, from the interface till G, how much is the vertical distance? Look at the vertical distance now. It is going to be 2.5 sine 30. So let me write over here. Area is going to be equal to 5 into 1 and H bar is going to be equal to 2.5 sine 30 degrees. Density for water, everyone knows, density has to be equal to 1000 kg per meter cube. If it is not mentioned, still you can take density as 1000 kg per meter cube. You are having M over here. Find me the value of M. Please start. I know the question might be slightly difficult, but it is a question which is covering entire hydrostatics on flat plates. Chaliye, use all these values. I have given you density, I have given you area, I have given you H bar. Get me the value of mass. Please be quick. Please don't expect me to write every step and all. At least problems you do parallelly with me. Notes you are not writing, I understand, but at least problems you can do. Very good, Yash Patel. Perfect answer. Maheshwar Reddy, I'll come to your answer. Soumya Patil, please check. The answer you're supposed to get for mass, the answer you'll get for mass will be equal to some 9622 kg approximately. 9622 kg approximately will be the answer. Okay, I'm seeing fine. 9600 is also fine. I'm seeing a lot of calculation mistakes over here. Numbers are same, but decimal places are shifting. Please check. Okay. Fine. Harika, very good way of answering. Per meter is very good. You people are having some problems with geometry. Now I'm coming to the geometry part over here. Some of you are not understanding how the value of what do you call this distance is equal to 3.33. Very quickly I'm discussing. Please look over here. You're having a triangular loading on OA. You're having a triangular loading on OA. If it is a triangular loading, what will happen? Your centroid of the pressure prism will be at what distance? This distance is going to be equal to 2/3 of length of gate. 2/3 of length of gate. We know this thing. For triangular loading, it is 2/3. This is something which you have studied in your basic mechanics also, right? 2/3 of length of this thing. Okay. I told you to please go through the centroids of standard geometries. Apart from this, some people are having difficulty with the value of h bar. H bar is very simple. You see, let us say I complete this particular diagram. This distance from the interface level till the point G, the distance is going to be equal to how much? This is going to be your h bar. This is going to be your h bar. How much is this distance? You see, this angle is 30 degrees. This angle also is 30 degrees. If both the angles are 30 degrees, that means I can say this value has to be equal to 2.5 sine 30. 2.5 sine 30 over here. Why is it difficult? Okay. Chaliye. Try this question again. Try this question. If you are finding some difficulty, try it again. I have shown you how to approach the question. It is all about drawing the free body diagram. On the left hand side, what I'm having is a free body diagram. On the right hand side, only one equation is there. This equation is there. This is the most important equation. If you understand this equation, it is the rest of everything is only calculation. Okay. Chaliye, let us move further now. Let us move further. This is just this slide is just a rough slide. Okay, this is just for rough work. Let us move further. I'm taking some questions from your literature, from your book. I'm taking some questions. One second, please. Page number 32, probably. Page 32 or 31, whatever it is. Look at question number 1. Look at question number 1. This is in your literature, chapter 2, question 1, please. In your literature, it is chapter 2, question number 1. Now, what does the question say? Which of the following pressure units represents the least pressure? Which of the following values is the least value he's asking? Okay. He has given you 4 options over here. First option over here is millibar. Millibar. Second option over here is 1 mm of mercury. 1 mm of mercury. Third option he has given is Newton per mm square. Fourth option he has given is kgf per centimeter square. The purpose of taking this question is especially for this particular unit, kgf. Chaliye. How to approach these kind of questions? Very, very simple question. Okay, which is the least value he's asking? Now, whenever you are approaching these kind of questions, try to convert every term into a common unit. For example, I'm going to convert everything in SI units. Everything in SI units. Milli means what? Milli means 10 power minus 3. Bar means what? 10 power 5 Pascal. So this is going to be equal to how much? 100 Pascal. I'm converting everything into Pascal now. If you remember, 1 mm of mercury was called as 1 torr. It is called as 1 torr. The value of 1 torr approximately is 133 Pascal. If you remember, Newton per mm square, 1 Newton per mm square is actually 1 MPa. It is 1 megapascal. This value is equal to 10 power 6 Pascal. Now, what do you mean by kgf? kgf over here stands for kg force. kg force. It basically means that the amount of weight of 1 kg on earth. It is basically weight of 1 kg on earth. Weight of 1 kg on earth. That means this is supposed to be equal to 9.81 newtons. So now I'm having this value as 9.81 newtons divided by centimeter square means 10 power minus 4 meters square. If you check this value, how much it comes out to be? It comes out to be 9.81 into 10 power 4. Newton per meter square means Pascal. Newton per meter square is Pascal. So these are the values I'm having for the corresponding ABCD in SI units. Now tell me which is the least value. I see that this is very high. This is even higher. This is fine. The least value over here is 100 Pascal. That means 1 millibar is supposed to be your answer over here. So whenever these kind of questions come where you're supposed to compare, then what you do is you convert everything into one standard unit. Okay. I hope you're getting this. Is a very simple question actually. This is quite simple. I'm taking one question from your literature. Next question I'm taking from literature over here is question number 9. See, I won't be taking every question. Whatever I feel you can do very easily, I leave that. Okay, the reason is I have to take some extra questions also. For example, the previous questions, what I have taken were extra questions. If I take all these questions from literature, then we won't have time for extra questions. Okay? Still, if you're having any doubts in the literature, you can let me know. I'll clarify those doubts. Question number 9 is a fine question. Actually, look for yourself. The question says a rectangular tank full to the top has its length, breadth, and height in the ratio of 2:1:2. The ratio of hydrostatic force at the bottom to that at any larger vertical wall surface is how much? Now, these kind of questions come in your examinations. Okay, wherever calculator is not allowed, in those kind of examinations, question number 9 kind of question can come. A rectangular tank full to the top has its length, breadth, and height in the ratio of 2:1:2. First thing first, let us draw a diagram. Let us draw a rough diagram. Imagine you're having a tank something like this. You're having a tank something like this. Inside you're having water filled in. Okay. Let us say this over here is length, this over here is breadth, and this over here is height. It is completely filled up till the top. Up till the top, it is completely filled. Now the question asked over here is, what is the, one more thing, he has given you length is to width, length is to width is to height is in the ratio of 2:1:2. 2:1:2. Now, you see, whenever these kind of ratios are given, my idea is take some parameter, for example, K. Take a parameter K and then say length is equal to 2K, breadth over here is equal to K, and height over here is again equal to how much? 2K. You take some parameter K, it will be easy for you to calculate that. Then he's asking what is the ratio of hydrostatic force on the bottom? Bottom plate over here means which plate? Bottom plate over here means this plate on the bottom plate versus the hydrostatic force on any of the larger walls, on any of the larger walls. Now, which is a larger vertical wall? If you see, there are two types of wall. One is length into height, the other is breadth into height. Of course, length into height is supposed to be the larger wall. So this over here is a larger wall. So let us say over here, the force is equal to F1 and over here, the force is equal to F2. The question is basically asking you, what is the value of F1 to F2 equal to? This is the question. I hope it is clear to all of you. Now, how do we answer this question? Let us start now. F1 kitna hai? How much is F1? F1 is equal to gamma into A1 times H1 bar. That is equal to how much? Gamma into. What is the area of this plate over here? This lower plate over here. How much is the area you're going to have? The area is B multiplied to L, is it not? The area is B multiplied to L. So B multiplied to L. H1 bar means exactly at its center from interface, how much distance are you going to have? The distance from interface, देखिए interface ऊपर से है, from top till this particular point, the distance is complete distance h. Complete distance h. Now, if you calculate this thing, put in these values 2k, k, and 2k over here. If you put these values, you are going to get over here 4 into k cube into gamma. This is the value you're going to get. You can check. Okay, b is equal to k, L is equal to 2k, h is equal to 2k. Similarly, let us look for the value of F2. Gamma into A2 into H2 bar is equal to how much? Gamma into. Okay. Don't type answer, but ask yourself what is the value of A2 you are going to get. Area कितना है इसका? Area देखिए L into H. L into H multiplied to H bar. How much is H bar over here? This particular plate center, let us say somewhere over here. How far from interface are you going to find its center? Exactly at a distance of h by 2. At a distance of h by 2. Now put in these values. How much are you going to get? Put in the values. Over here 2k, over here 2k, over here 2k by 2. That means this is equal to 4k cube times gamma. 4k cube times gamma. You're seeing F1 and F2, both of them are same. Therefore, the value of F1 to F2 over here has to be how much? It has to be equal to 1. Now, this is a worthy question for 1 mark. Okay, this kind of question you can expect for 1 mark in GATE examination as well as in IAS examination. I hope this was quite simple. Question number 5, people are saying they're having difficulty with question number 5. I find it quite a simple question. Okay. So if you want to take down, please be quick. Be very quick in taking down problems, okay? I'll take question number 5. I'll take question number 5. It is not that difficult. Still, let us see. 5th question. You're having a bulb. I'll just make a rough diagram over here. You're having a bulb, and then you're having some kind of a manometer over here like this. Okay. Let us say you're having a manometric fluid over here. Something like this. There's a certain point over here, point P. Let us say this is oil. This is mercury. Distance over here given is equal to 60. Distance over here given is equal to 10 centimeters, of course. He's asking pressure at P in terms of head of oil. P in terms of head of oil. Start from here. Start from here. Let us say this point is point A. Start from here. Come down up till here. So you can say from here the pressure is equal to 0. The pressure over here is equal to 0 exposed to atmosphere. You're coming down. So 0 plus coming down, इसलिए plus gamma mercury into how much height is it? 0.1 meters. Okay, you have reached till here. Listen now. Reaching till here is as good as reaching till here because you are having same continuous fluid and same horizontal level. Reaching till here is as good as reaching till here because you are having same continuous fluid and horizontal level. That means just by writing this much, I have got the pressure at this particular point. From this point to P, what are you doing? You're again coming down. If you come down plus Now you're coming down with oil. So gamma of oil multiplied to height over here is equal to 0.6 meters. This is the value of pressure at P. But he does not want pressure at P. He wants P divided by gamma of oil, therefore divided by gamma of oil. This is the answer. Like a very simple question. Not that difficult at all. Those who are having difficulty, you can take a snapshot. Calculation बाद में करो, अभी नहीं. Okay. You can do the calculation later on. Question 13 I'm taking. Question 30 from your literature. Those people who are thinking that assertion reasoning questions are only for IES, let me tell you, GATE has started to ask assertion reasoning question. Okay, recently I have seen assertion reasoning question in a different branch. Okay, probably in electrical branch I have seen an assertion reasoning question in GATE examination also. So please be prepared. Many times people are asking me regarding how much is sufficient. See, there is nothing sufficient actually. How much ever you study, it is not sufficient because this is competitive examination. In competitive examination, how much you study is not a concern at all. Sometimes others are also studying more, right? So keep practicing how much ever you can. The book I'm having right now is this book, volume 1 book. For civil I'm having right now, but same questions are there in mechanical also, don't worry. Achha, those who don't have question number 13 in literature, those who don't have question number 13 in literature, let me write. Statement 1 says, at great depth, the vertical distance between the center of pressure and center of area of immersed surface becomes negligible. Of immersed surface becomes negligible. Statement 2 says, depth of center of pressure is independent of density. Okay. See, if you don't have these questions, you can at least go to the PDF you are given now. From there you can get the questions at least. Try doing that next time onwards. Actually, this is an assertion reasoning questions. I am telling you, GATE people, please be prepared for assertion reasoning questions also in GATE examination. There are possibilities now for assertion reasoning questions. Actually, look over here. Statement 1. My logic for assertion reasoning questions is, listen carefully. Okay. You see, as engineers, we understand equations and diagrams better than statements. फिर से बोल रहा हूँ, सुनिए. As engineers, we understand equations and diagrams better than statements. So whenever you have these statement questions, if you can convert into equation or convert into diagram, please do that. That will be helpful for you. For example, statement 1, at great depth. Great depth का मतलब क्या हो गया? Great depth बोलते कि you should understand that the value of h bar is increasing. Vertical distance between center of pressure and center of area. Vertical distance between center of pressure and center of area. What do you mean by this thing? Center of pressure and center of area vertical distance. Imagine you are having some plate like this. This was h bar. This was h star. Vertical distance between center of pressure and center of area basically means this entire thing over here is saying h star minus h bar becomes negligible. Becomes negligible means it is going towards zero, approaching zero. Is this statement correct? You see, I'm trying to convert now into diagram and equations over here. As I keep increasing h bar, Is the value of h star minus h bar tending towards 0? Yes, because recall, what is the value of h star minus h bar equal to? It is equal to I sine square theta upon area times h bar. Let us say you are keeping on increasing h bar. You are keeping on increasing h bar. Okay, as you keep increasing h bar, this value is going to become negligible. That is correct. Okay, statement 1, correct. Statement 2, depth of center of pressure. Depth of center of pressure means what? H star is independent of density. Mathematics में independency को हम not a function of बोलते हैं. In mathematics, independency you can say is not a function of density. Check. H star formula you check. H star is equal to H bar plus, please don't mind my handwriting now, sine square theta upon area times H bar. Check, is H star in any way a function of density? कहीं भी density लिखा हुआ है यहाँ पे? नहीं लिखा हुआ. That means this statement also is correct. But is this statement having a reasoning effect? Is there any reasoning effect over here? I don't see any reasoning effect. Okay, so I can say there is no reasoning effect whatsoever from statement 2 to statement 1. That means if I know statement 2, can I conclude from their statement 1? Reasoning effect का मतलब क्या है? Statement 2 I know. Can I from statement 2 approach statement 1 as a conclusion? No, that is not there. Since it is not there, the answer for this is statement 1 correct, statement 2 correct, but no reasoning effect. Therefore, the answer over here is supposed to be B. The answer over here is supposed to be B. I hope this is clear to all of you. Smita Gaikwad, it is not eccentricity. Eccentricity is along incline. Eccentricity is along incline. This is vertical distance he's saying. Okay. So this is some question you are having. Let us move further now. You can take down a snapshot of this if you want. Though my handwriting is not that clear, but I hope the understanding is still fine. Next, I'm taking a question from your literature. This is page 39 in my book. Probably when I say 39, plus or minus 2 you'll find questions. Mostly minus 2 only, not plus. Okay, minus 1 or minus 2 you'll get the page. I'm taking question number 8 from here. I'm taking question number 8 from here. Okay. Some books 37 page number. So question number 8 I'm taking. This is worth 2 marks in your examination. This question is worth 2 marks. It never appeared. It is worth 2 marks in your examination. Read the question for yourself once. This question will be present in everyone's book. Okay, GATE and IAS, both the books, this question should be present. Read it for yourself once. The question says a vertical gap of 23.5 mm wide, actually width should be there, width of infinite extent contains pile of specific gravity 0.9 and viscosity 2.5 Newton second per meter square. A metallic plate 1.5 meter cross 1.5 meter cross 1.5 mm weighing 50 newtons is to be lifted through the gap at a constant speed. अपनी बुक में कांस्टेंट स्पीड को अंडरलाइन कीजिए. प्लीज अंडरलाइन कांस्टेंट स्पीड इन योर बुक. Estimate the force required. You see, why is this constant speed important? Okay, you will come across these kind of questions in other subjects also. You will come across constant speed kind of questions later on in drag and lift also. Remember, whenever speed is equal to constant, acceleration equal to 0. Whenever acceleration equal to 0, straight away apply equilibrium. Okay, straight away apply equilibrium. The body is moving, but still it is in equilibrium. The moment you see questions on constant speed, terminal velocity, your idea should be straight away to approach equilibrium concept. Chaliye, let us draw this diagram. He's seeing a vertical gap. He's saying a vertical gap is there. A vertical gap is there. So for example, let us say I'm having over here, some vertical gap like this. Let us say this is something which is fixed. This is something which is fixed. Next, there is a particular plate over here. There is a particular plate over here. Suppose this is a plate you're having. This is a plate you're having. And then you're having some fluid around. Suppose you're having some fluid around. There is some fluid present over here. I hope you are getting an image. Okay. Now he's saying that this plate is supposed to be lifted. This plate is supposed to be lifted with certain force F. The plate is supposed to be lifted with certain force F, while he has mentioned to you this distance is equal to 23.5 mm. This distance is 23.5 mm. Okay. And he has mentioned to you that this fluid is having certain viscosity. Viscosity is equal to 2.5 Pascal second. The specific gravity of the fluid S is equal to 0.9. That is implies density is equal to 900 kg per meter cube. 900 kg per meter cube is the density you're having. Furthermore, when you're lifting this up, it should have a constant velocity. That velocity is supposed to be equal to how much? It is supposed to be equal to 0.1 meters per second. Estimate the force required over here. How much is the force required over here? Now listen to me. When I have drawn this thing, I have made an assumption. That assumption I have made over here is this plate is kept exactly at center. Why did I make that assumption? There is something known as standard assumption concept. In any examination, any subject, you should be knowing there is something called a standard assumption. What do I mean by this thing? Whenever there is some kind of data insufficiency in a particular question, okay, that means in this question, he did not say exactly at what distance from each plate did he keep. That time you should go for the simplest assumption. Yaad rakhiye, standard assumption is mostly simplest assumption. Simplest assumption. Ab kya hai simplest assumption? Aap sochiye. If you ask 10 people, at least 8 will say, let us keep it the center. That seems more logical to you. That is what you are supposed to do. Okay. All these things will be developed as you keep on doing questions. Furthermore, he has also mentioned to you that this is going to have a certain cross section, that is 1.5 meters cross 1.5 meters cross 1.5 mm. This is what he has mentioned. Okay, all these things are mentioned in the question. Now, when you are lifting this plate up, first thing, ask yourself how much gap you are having over here. What is this distance equal to? Of course, this distance cannot be 1.5 meter. This cannot be 1.5 meter. It can only be 1.5 mm. This can only be 1.5 mm. Okay, if this is equal to 1.5 mm, ask yourself next thing, how much is this gap over here equal to? How much is this gap over here equal to? Ab dekhiye, 23.5, from 23.5 you have removed 1.5. How much is left? 22 is left. Half you give to the left hand side, half you give to the right hand side. That means over here you are having 11 mm. Likewise, you are having over here also 11 mm. 11 mm you are having. Perfect. As you are lifting this up now, as you are lifting this particular plate up, let us draw a free body diagram over here itself. As you're lifting the plate up, you're going to have a velocity gradient developed. Since he mentioned viscosity, you have to consider the velocity gradient. Shear stress aayega. It will come now. Now, how much shear stress will be there? You see velocity gradient first of all. You are supposed to have some velocity gradient. Again, I have made a standard assumption over here. And this time the standard assumption is linear velocity profile, because that is the simplest assumption I'm having. There is going to be some shear stress developed over here. So if I draw the free body diagram, I'm going to have weight coming down, force applied over here. Since I'm pulling this up, shear force on the plate will come in the downward direction. Let us say this is Fs, this also will be same Fs. One more thing, since this plate is occupying some space in this particular fluid, it is going to experience one more force, and that force is the force Fb. Now I can say, since velocity over here is constant, implies acceleration over here is zero, implies equilibrium. Since we are having equilibrium, I can say over here, summation of vertical force has to be equal to zero. Okay, same story. Actually, I did not draw over here. Same story will be repeated over here also. Please understand. Okay, so summation of Fy over here is going to be equal to zero. So what do you have? Upward forces are F plus Fb have to be equal to downward forces, that is weight plus 2 times Fs. That means the value of F has to be equal to W plus 2 times Fs minus Fb. W plus 2 times Fs minus Fb. You know the value of weight. Did he give you the value of weight? Yes, he gave the value of weight. I did not write over here. The weight of the plate is equal to 50 newtons. 50 newtons. You know the value of weight. You don't know the value of Fb, you don't know the value of Fs. How to find out? First, let us say Fb. Fb has to be equal to gamma of fluid multiplied to volume of fluid displaced. अब देखिए gamma of fluid is equal to how much? Density is given. So density multiplied to G will give you gamma. Volume of fluid displaced over here is equal to 1.5 meters cross 1.5 meters cross 1.5 mm. From here you can get the value of Fb. Okay. Chali, first of all, do this much. Get me the value of Fb quickly. Okay, 29.798. Let us say 29.8. 29.8 newtons, let us say, is the value of Fb. 29.8 is the value of Fb. Okay. Fs will be equal to how much? How much will the value of Fs be? I'll do one thing, I'll slightly, one second. Let me cover this thing over here itself. How much will the value of Fs be equal to? The value of Fs has to be equal to shear stress multiplied to shearing area, is it not? The value of Fs has to be equal to shear stress multiplied to shearing area. So Fs is equal to, Newton's law of viscosity says, mu into du by dy multiplied to shearing area. So Fs has to be equal to, mu is equal to how much over here? The value of mu is given 2.5. This is mu. Du by dy, very, very simple. Please look over here. Du, यहाँ पे कितना u है? The u you are having over here is equal to how much? 0.1 meter per second. What is the u you are having over here? 0. So du is equal to 0.1 minus 0. dy, gap कितना है? The gap between is equal to 0.011. multiplied to shearing area. Shearing area is equal to how much? Please look carefully now. You're having a height over here equal to 1.5 meters cross. The width perpendicular to your screen, you can't see that thing. You have to imagine perpendicular to screen. That is also equal to 1.5 meters. 1.5 meters. From here, you will get the value of Fs. You will get the value of Fs. Chaliye. Get me the value of Fs also quickly. See, you're having calculators. Please don't do calculation mistake. I'm finding many calculation mistakes over here. Answer should be 51.13. I believe this is the answer. 51.13 newtons. ठीक है. Now, in this particular equation, you put the value of FB and the value of Fs. Get me the answer. Get me the value of F from here. Put in the value of FB and Fs. Get me the value of F from here. One 122.47 newtons. Find the Fs means shear force over here. Chaliye. Now look over here. Some people are having a doubt that I have taken. Okay, imagine this is a plate I'm having. Some people are having a doubt. I have taken this shearing area, this shearing force and this shearing force on this side and on this side I have taken. So when I'm lifting this plate up, this side I have taken, this side I have taken. I have not taken over here. People are having a doubt. Why have I not taken over here? Similarly, why have I not taken at the backward face? Why have I not taken over here? Good question that is. You see, the plate, that fixed plate, look at the fixed plate. This is fixed plate. This is fixed plate. The fixed plate is over here of infinite extent. That means there is no wall available in front. Imagine there is no wall available in front of this plate. In front of the plate, there is no wall available. If there is no wall available, let us say distance over here is infinite distance. So there is no shear stress developed on this wall and this wall. Only on the larger walls you are going to have shear stress developed. Think over it again. Okay. I took it twice because I'm having two faces. Now I have two faces, therefore I have taken twice. So with this, I'm ending the concept of fluid statics. Entire fluid statics is done with. You practice questions. There are many questions. You keep on practicing, and you have difficulty, you can let me know. I'll help you out with the difficulty. Now I'm starting the next topic. This topic over here is fluid kinematics. Fluid kinematics. Okay. Now forget about fluid statics for some time. Listen to this thing. This fluid kinematics is actually a very interesting topic. At the same time, very difficult topic. Since it is a difficult topic, people have started to believe that fluid kinematics is not interesting at all. That is wrong. If you get the feel of the subject, you will like this chapter the most actually. I'm telling you, if you are able to feel the subject, if you are able to feel the mathematics in this subject, you will like this chapter the most. Take it. But before I start fluid kinematics, I'm not straight away going to start fluid kinematics. I'll spend some 10 minutes in understanding some mathematics over here. Let us see some mathematics. Okay. This is whatever I'm discussing for 5-10 minutes is not a part of fluid mechanics. It is a part of mathematics. The first question over here. What exactly do we mean by function? What do we mean over here by the word? In mathematics, when we use the word function, What is the physical meaning of function? The physical meaning of function as such is dependency. You can say function means dependency. Dependency. One more word you can use for function, or one more phrase you can use for replacing function is varies with respect to. Varies with respect to. So when I say, for example, I say, let us say, y is a function of x. So basically it means y depends on x, or y varies with respect to whom? X. That is the basic meaning of function. Now imagine y is a function of x, for example. When y is a function of x, if I want to know what is the value of dy, what is the value of dy? How do I find this value? The logic is simple. When y is a function of x, the value of dy is basically going to be equal to, dy is going to be equal to the rate of change of fx multiplied to dx. Multiplied to dx. What is the meaning of this thing? Try to understand using a graph. Imagine this is y, this is x. I'm having some kind of variation over here. Imagine at some particular point, I come up to you and ask, at this particular point, what is the value of dy? Let us say for a small distance, how much is a dy value over here equal to? You will say, wait for some time, I'll give you the value. You will say that at this particular point, find out at what rate this function is changing. Let us say that function is changing at this rate. So let us say this is rate of change. This is rate of change. But rate of change is not sufficient. You see, you want dy, no? You want this much distance, dy distance. This is distance dy you are having. Okay. I gave you, let's say you are finding rate of change, but then you have to multiply rate of change with this distance also. The distance is equal to what? Dx. This distance is equal to dx. This distance will be equal to dy then. This is a logic. From here only you get that logic that the value of f dash of x. Chali, you take f dash of x, how much will it be equal to? Push dx over here. F dash of x is equal to dy upon dx. I hope all these things are clear to you. This is simple because this is called as function of a single variable. This is function of single variable. Where does the problem come in? Our subject of fluid dynamics mostly deals with functions of multiple variables. For example, let us say there is a particular parameter u, which is a function of x and y. You are having a parameter u, which is a function of x and y. Now, if I come up to you and ask, what is the value of du equal to? I will say this is difficult. Why it is difficult? Previous case I could understand easily, but this case I'm having multiple things over here on the right hand side. So for this, let us do one thing. Let us create some kind of analogy. Imagine again that I'm having a particular graph. I'm having a particular graph. Let us say this is x, this is y over here. Suppose there is some particular point over here. This point is A, and there is some particular point over here. This point is B. The distance from A to B, is a very, very small distance. In horizontal, it is equal to dx. In vertical, let us say it is equal to dy. The distance from A to B in horizontal is dx. In vertical, it is dy. Du basically means when the parameter u, please listen to this, have some patience, okay? You will appreciate the concept later on once we enter into fluid kinematics. Please be patient and listen to this thing. At point A, you are having some value of u. You are having some value of u. Let us say a parameter, you are putting it in a field. Let us say in a field, it started from point A. It is exiting from point B. When you exited from point B, it is exiting from point B, it is having a change now. That is u plus du. My question over here is, what is the value of this du? This is the question we are having. What is the value of du? So now think logically. Imagine yourself, you yourself is this parameter u. I ask you to go from some point A to some point B. So how do you go? When you want to go from some point A to point B, you're not just going to fly off like a crow from point A to point B. You will say, let me break this thing into simpler part. You will tell yourself, let me do one thing. Let me go from here to here, create some transit point, some intermediate transit point. Then let me go from here to here. Let me go from here to here. So when you're going like this and then you're going like this, you are going to say that while I'm going like this, listen carefully, while I'm going like this, my parameter u is going to change only with respect to x-axis. For me, the value of y along this thing is constant. Therefore, I'm having no change with respect to y whatsoever. So now I will have a change over here. Sorry, I'll have a change over here as u plus a small change in u, but only with respect to x over here. That is going to give you something known as del u with respect to x. Del u with respect to x. This is where the concept of partial derivatives come in. You see, when you're traveling from here to here, who is constant over here? Y is constant over here. Then you are going to move from here to here. You're going to move from here to here. While you are traveling from here to here, you are saying the value of x is constant. For me, now the change will come only with respect to y. So whatever you are having, you'll still have u plus del u with respect to x, still you will have. Along with that, you are going to have one more thing, that is del u with respect to y. Both these things combined are going to give you the value of change, complete change. I hope you are following this thing. So whenever I'm having a function of multiple variables, I'm going to say the value of du is going to be equal to change with respect to x plus change with respect to y over here. Change with respect to y over here. Okay. Actually, this is not exact answer. This is approximate answer. One more change will come. That is not required. That is not required. One more extra change will come. For us, only this much is sufficient. Now, what is this change with respect to x going to be equal to? This change with respect to x is going to be equal to, now go for this thing. Now go for this thing. Look at this. This is the first principle in calculus. This change is going to be equal to rate of change multiplied to dx. So it is going to be rate of change. This rate of change we are going to write as dou u upon dou x multiplied to dx plus this is going to be equal to how much? Again, rate of change. Rate of change over here is dou u upon dou y. With respect to y, इसीलिए dou u upon dou y multiplied to dy. This is basically the value of your du. I hope you are following all these things. So the logic is very simple. When do you go for partial derivatives? You are going to move for partial derivatives whenever you are going to have functions of multiple variables. Function of single variable is easier to imagine, but applications will be lesser. Functions of multiple variables, slightly difficult to imagine, but really beautiful. Very, very beautiful concept. Okay. But this function of multiple variables, even though it is slightly difficult, it is going to have many applications. Remember, nothing in universe varies with respect to only one variable. Everything has many variables. Multiple variables are going to be there. Okay. I hope you are following all these things. Let me first of all tell you the terminology I use. This I call as del. And this I call as do. As far as I know, so whenever I teach in Maharashtra, people over here this call it daba. Daba hai ya dappa hai nahi malum meko, lekin daba bolte hain. Okay, daba. I call it as do. I call this as del. You please be convenient with my terminology. In my flow of teaching, I will always use these things only. I won't use daba. Del bolunga, do bolunga. You have to understand. Okay, no? Challiye, I hope all these things are clear to all of you. Now, if you want, you can take this down because these things are not a part of fluid mechanics. So you can just write down if you want some things. Okay. Please be quick if you're writing down. See, if you're having difficulty with this thing, I can't go into details, you see, because even though I like this topic a lot, but I can't go into detail because it's not a part of my subject though. What I would recommend you to understand is, remember, whenever you're having, let us say, a function of something like this, x, y, z, and t, for example, if anyone asks you what is the value of du, then you are going to say this u is going to experience a change with respect to x. It is going to experience a change with respect to y. It is going to experience a change with respect to z. It is also going to experience a change with respect to t. Okay. So when complete change is equal to partial changes, treat these things as partial changes. Now, how much is these things? Remember, logic is very simple. Change is going to be equal to rate of change multiplied independent variable. That means this value will be equal to how much? Rate of change. So dou u upon dou x is rate of change multiplied to dx. Likewise, this value will be equal to rate of change dou u upon dou y multiplied to dy. This is rate of change multiplied to dz, rate of change multiplied to dt. ऐसे लिखेंगे आप इसको. This is how this entire change is going to be experienced. I'm going to use all these concepts later on. That time I won't be discussing. If you are finding it difficult to understand over here, probably don't mind me saying this, but this is truth. Probably you have not studied mathematics perfectly in calculus part. Okay, never mind. At least you understand this much. Try to remember this much. You can manage our subject very easily then. Apart from this, there are some more misconceptions in calculus. There are some more misconceptions in calculus. Achha, someone is asking what is a graph for 3 or 4 variables. We don't draw a graph for 4 variables and all. You just have to visualize these things. 3 variables, I can create a 3D diagram. That is not required. There are some misconceptions in calculus. For example, let me give you a small question over here. The question is, some parameter u is equal to 3x cube into y square plus 4y cube. Example sake. Some equation I'm writing like this. I ask you to give me the value of dou u upon dou x is equal to how much? Please quickly answer this thing. Dou u upon dou x is equal to how much? Quickly. बहुत simple question है. Dou u upon dou x कितना है? Voice is not. What is the value of dou u upon dou x equal to? Very good. Okay, very good. Dou u upon dou x means you are going to differentiate only with respect to x. Okay, you are going to treat y as constant. If you treat y as constant, for you this is constant, this is constant. This entire thing has become constant for you. That means this, you will say differential of this thing is 0, you'll say. So now the value of dou u by dou x, if you see, will be equal to 3x cube differential is equal to how much? 9x square multiplied to y square. You go over here, you see this is constant for this particular case, you will say nothing is there. Fine. Okay. Now take one question. Let us say this question over here. Dou u by dou x is equal to 9x square y square. The value of u is equal to how much? This is the question. Chali, now answer me this thing. Please answer me this thing. Answer me this thing. Dou u by dou x is 9x square y square. I'm asking you to give me back the value of u. क्या मिस्टेक कर रहे हैं आप फिर से डिफरेंशिएट कर रहे हैं. Some people are differentiating again, that is wrong. Okay, Basir Reddy, fine. Here you people are having problem. I did not get even a single correct answer till now. Someone is saying integrate. I know, sir, I have to integrate. I'm asking you to integrate. Very good. Atul Anil, you are the only person who has given me correct answer. Chali. Okay, stop answering now. I'm not getting correct answer anyway. See, one thing you do, okay, please go through your calculus once, whatever you have studied probably in your college. You go through that calculus once. Please stop answering now. Stop answering. Listen to this thing. If I integrate this thing, I'm going to get the value as 3x cube y square plus, let us say, constant c. But this is a problem. You are not supposed to write this constant c over here. Why are you not supposed to write the constant c over here? Because this is the integration of a partial derivative. Partial derivatives integration is there. That means this constant c basically, in place of that, you can say, probably I was having a function of anything apart from x initially, whom I probably treated as a constant. Example you want to see, you can see over here. That is why I have taken initially this particular case. Imagine over here, initially what you have done, you have treated a pure function of y as a constant. That is what you are going to acknowledge now. You are going to say, probably before I was having a function only of y, something apart from x, only of y, whom I have treated probably as a constant. तो उसको acknowledge करना चाहिए, उसको consider करना चाहिए, f of y होना चाहिए यहाँ पे आंसर. ठीक है? So you are supposed to say u is equal to this much. How much is f of y? That is none of our business. How much is f of y? We cannot find out at this stage. For that, some more conditions are required. But you should at least mention this thing. Very quickly, tell me if the value of, let us say, dou u by dou x is equal to 9x square y square t. What is the value of u? चलिए अब तो आंसर करो कम से कम. Please answer for this question. T is also there. There here, T is also there. Very good. Now, if I integrate this thing, I'm going to get 3x square, x cube y square t plus. I have to say probably a function of y and t I have treated as a constant. So plus a function of y and t. Don't write f of y separate plus f of t separate. वो गलत हो जाना फिर से. You should write f of y plus t लिखना चाहिए. If you write f of y, that means only purely a function of y is there. क्यों ऐसा क्यों? It can be, let us say, y cube t square. ये भी हो सकता. Okay. So write f of y and t. I hope this is all clear to you. All these things are important. Please understand. From whatever mathematics I'm discussing, you are going to have questions in your GATE examination also. Not mathematics, I'm saying fluid mechanics. Questions in fluid mechanics will come. Okay. I hope you're understanding all these things. Chaliye, stop answering for some time. Chaliye, let us now move further. One more concept I want to discuss is the concept of acceleration. Quickly. Concept of acceleration. Remember, there are two types of acceleration. Okay. In linear acceleration only, you're going to have two types of acceleration. One type of acceleration is called as your tangential acceleration. Tangential acceleration. The second type of acceleration is called as centripetal or radial acceleration. The purpose of first acceleration, tangential acceleration, is to represent, or it is taking care. Let me do one thing. Let me write in a different way. Look over here. Let me slightly go into detail and mention this thing. Chaliye. All of you know that velocity is a vector quantity, right? Velocity is a vector quantity, and acceleration vector is equal to dv vector divided by dt. I can write over here. This is equal to d by dt of mod v into v cap. D by dt of mod v into v cap. I can write. Now go for in that UV rule. You might have studied UV rule, no? If you go by UV rule, you are going to have mod v into dv cap by dt plus v cap into d mod v by dt. D mod v by dt. If you look at this particular part, Achha, first of all, I hope all of you understand mod v means magnitude, v cap means direction. If you look at this particular part, what is this part talking about? It is talking about change in direction of velocity with respect to time. This acceleration is known as centripetal or radial or normal acceleration. So what do you mean by normal acceleration? The acceleration which talks about change in direction of velocity. Okay, it talks about change in direction of velocity. Change in direction of velocity. Okay. Now coming to this acceleration. What is this acceleration over here talking about? This acceleration is talking about change in magnitude of velocity with respect to time. This is called as tangential acceleration. It is now going to speak about change in magnitude of velocity. Change in magnitude of velocity. Okay. So please try to just understand there are two types of acceleration. All these things I'm going to use later. Okay. There are two types of acceleration. One more acceleration is there. Under tangential, one more acceleration is developed. That acceleration is called as Coriolis acceleration. Mechanical people might have heard of this thing from their theory of machines concept. There is something known as slotted lever mechanism in theory of machine. Slotted lever, quick return mechanisms, and all those things are there. Over there, they have one more acceleration called as Coriolis acceleration. What do you mean by Coriolis acceleration? Okay. Under tangential, an extra acceleration known as Coriolis acceleration is present. When is it present? Please understand this thing. To understand this Coriolis acceleration, understand that. Imagine you're having some lever. On this lever, let us say you're having a particular ball. You rotate this ball. So this ball is going to now trace a circle. Let us say, I'm sorry for troubling you with all these things. Okay, but if you understand all these things, for me, teaching the subject will be easy later on. Generally, people come without all these ideas. When I use this concept in fluid mechanics, that time they'll be surprised what is happening. That is why instead of being troubled for some 8-9 hours, be troubled only for half an hour. Later, you can use all these things. Now, if this ball is there, if this particle is there, you are rotating this thing, it will trace a circle. This is circular motion, fine. But imagine that this particle, imagine that this particle is having a liberty to move along this particular lever. And then you're rotating this thing. If it is able to move and it is able to rotate, that time what will happen? Please understand. 1 second. Imagine it is able to move like this and you're rotating this thing. That time the particle will move like this. It will come over here. Particle will move like this, come over here. So now what is happening? Your particle is not just going in circular motion, it is going in spiral motion. That means your velocity is varying with respect to radius also. As you keep on moving, you are going to have different radius also. That is when Coriolis acceleration is present. It is present when the radius of the particle changes with time. Okay. This much you remember. Values I'll give you later on. Just understand that there is something called as velocity. It is a vector quantity. Listen to the story carefully. There is something called as velocity. It is a vector quantity. Its change is represented by acceleration. But since velocity is a vector quantity, it can experience change in magnitude as well as in direction. Magnitude's headache is taken care by tangential acceleration. Direction's headache is taken care by centripetal, radial, normal acceleration. In tangential acceleration, sometimes you'll be troubled with a case where you are not going to have circular motion, you are going to have spiral motion. Derivation I'm not doing. I used to do derivation previously. People were troubled a lot with derivation. That is when I stopped doing all these derivations. And as such, they are not a part of fluid mechanics. They are a part of advanced mechanics. Okay. So no need of derivations and all for you. You just need to know that under tangential acceleration, a particle, when it is moving in a circle, tangential is fine. You will be having some acceleration called as R alpha tangential. Lekin, imagine the radius of the particle also is changing. So along with R alpha, you are going to have something called as Coriolis acceleration. ये कब आएगा? ये आएगा तब. This will come when R is changing. This is coming when omega is changing. That is, rotation velocity is changing. Then you are going to get this. This you are going to get when R is changing. This much you remember. It is sufficient. I'll manage everything from here onwards. Okay. Chali. Till here, whatever I have discussed was not a part of fluid mechanics whatsoever. You still have difficulty, you please go through some literature for mathematics or basic physics. I recommend don't go through literature. Just whatever I said, try to remember that at least. Because once you start reading books, the problem with students nowadays is they have lost a culture of reading books. Reading book actually is the essence of gaining knowledge. You have lost that culture. Accept kar lo usko. Okay, accept it. You have lost the culture of reading book. Now when you open book, you find it very difficult. You cannot organize the subject when you open the book. That organizing headache is important. That is difficult. So for that, I'll take care of organizing. You just try to remember these 2 slides. Itna yaad rakho basa. Baki I'll take care. First, you remember this slide over here. Whenever you're having functions of multiple variables, change is something like this. Change is something like this. Okay, and this is how you are going to calculate the change. And when you integrate this thing, you are going to get something like this. This I hope you have understood. Second, whenever I use the words these centripetal, tangential, Coriolis, don't be surprised. Okay, सुबह सुबह 6:30 उठ के सरप्राइज हो जा रहे हैं आप, अच्छी चीज नहीं है वो भी. ठीक है, don't be surprised. You just try to understand कि when is this going to happen. This much is sufficient. Snapshot ले लो. Okay, let us now move further. Let us move further. I'm officially starting the chapter of fluid kinematics now. Fluid kinematics. Fluid kinematics. First of all, let us define this chapter. Define what is fluid kinematics. How do we define this fluid kinematics? Till the previous chapter, statics, the fluid was in static condition. But from here onwards, the fluid is moving. But what we are doing is, we are not going to analyze the entire motion. You see, motion analysis is slightly difficult compared to statics. So we are going step by step. First, what we are doing is, to analyze the motion, we are not taking concern of forces. We are just talking about its kinematic parameters. Kinematic parameters means parameters which are independent of forces and inertia. Okay, they will be independent of mass and all these things. Okay, those kind of parameters are discussed over here. So I can say the study of fluid flow in which the forces causing the flow are not taken into consideration. Are not taken into consideration. The study of fluid flow in which the forces causing the flow are not taken into consideration is known as fluid kinematics. Okay. Achha. So in this chapter, you are going to study kinematic parameters. Apart from kinematic parameters, you are going to have something known as hydrodynamic parameters also. So first of all, let me see what is kinematic parameter. Kinematic parameter. Kinematic parameter. Parameters dealing with motion. But independent of inertia. Independent of inertia. Inertia over here basically means mass. Remember, there are two types of inertia a body can have. One is called as linear inertia, which is mass. Other is called as rotational inertia, which is known as mass moment of inertia. Okay. So by inertia, I mean over here linear inertia. Linear inertia means mass. Okay. Parameters dealing with motion but independent of inertia. Those are called as kinematic parameters. One rule for kinematic parameters is you take any kinematic parameter, its dimension should be in the form of m power 0. L power something might be there, t power something might be there, but m power 0 आना चाहिए. For example, you take velocity, you take acceleration, you take displacement, you take rotation, anything you take. Are you going to have kg over there? देखिए velocity units क्या है? Meter per second square, meter. This is going to be radian per second. Everywhere you are seeing kg power how much is? 0. It should be independent of inertia or mass. Therefore, you will see m power 0 in any kinematic parameter. Apart from kinematic parameters in fluid kinematics, sometimes you will come across hydrodynamic parameters. Hydrodynamic parameters. Hydrodynamic parameters. You see, hydrodynamic parameters are basically, they don't deal with motion. They don't have to deal with motion. But these are some parameters which are important in fluid flow. Example, pressure. You see, in a fluid flow, pressure variation can take place. If you are studying advanced fluid flow, temperature variation can take place. So temperature also is a very good hydrodynamic parameter. Density is a hydrodynamic parameter. Now you see, in these cases, m power 0 need not be always there. M power something can come. For example, pressure is Newton per meter square. Mass power is there. Density, mass power is there. These kind of parameters are also sometimes discussed in fluid kinematics. Please understand this thing. These kind of parameters also can be discussed sometimes. Now, let us talk about the flow of topics. What are the sequence of topics we are going to discuss? See, fluid kinematics is there or not there in GATE 2021. It is there, sir. There is no examination that can be there without fluid kinematics. They have rephrased in civil department, they have rephrased fluid kinematics in a different way. Okay. Without fluid kinematics, there is no continuity equation. Without continuity equation, you can never discuss regarding Bernoulli, flow through pipes, nothing can be discussed. Okay. For some time, please keep quiet. I assure you, whatever you listen, you will understand. Only thing is, you should put some effort from your side also. I assure you, you'll understand. You just listen to my story. Okay. Now we are going to discuss regarding what all are the various things we will have in this particular chapter. Flow क्या है? देखिए, organizing the subject is important. If you are not able to organize, you will spend lot of time wasting in remembering the subject. पहले organize कर लीजिए. I am going to say that fluid kinematics is going to have 3 parts. For me, fluid kinematics has 3 parts. Three parts. The first part over here will be the most lengthy part and the most important part. Most important part is the first part. Okay. This first part over here basically deals, please don't comment. Please don't write anything now. Just listen. Whatever is there, you can ask me in the doubts class. Okay, this first part over here is going to deal with basics of fluid kinematics. Over here, you'll have very few topics, but you will be having very lengthy topics. These will take a lot of time actually. Okay, we will start first of all with approaches. Fluid kinematics studying is slightly difficult. Therefore, we are going to have multiple approaches. There are two approaches. One is called as Lagrangian approach. One is called as Eulerian approach. We'll see all those things later. After approaches, you will discuss regarding the most important parameter in our subject. The most important parameter in fluid kinematics is going to be velocity. Please recall, in statics, the most important parameter was pressure. याद रखिए इसको. Statics में क्या important था? Pressure important था. In kinematics, who is important? Velocity. Later on, when we discussed flow through pipes, over there, discharge and head loss will be important. Okay, statics, pressure. Kinematics में velocity. Later on in flow through pipes, the most important parameter over there will be discharge. वहाँ पे discharge or of course head loss will be important. चलिए. So first we'll start with approach, then we'll discuss the concept of velocity. After discussing the concept of velocity, immediately we'll see classification of flow. Classification of flow. All of you might have studied something called a steady, unsteady, uniform, non-uniform. All those things we'll be discussing over here. Okay. After classification of flow comes the heart of entire fluid mechanics subject. This is the most important part throughout fluid mechanics. Without this, there is no subject. Okay. This is known as continuity equation. Very simple equation. Continuity equation. This is continuity equation. After continuity equation comes the concept of acceleration. Sometime back I troubled you with some acceleration terms now. All those things you'll be seeing over here. This will be the first part, basics part here. Okay. Achha, after approaches, velocity, classification, all those things, come to the second part. What do we do in the second part? Why is the second part different from the first part? The first part is completely mathematical. Second part is visualization part. अब आप देखना चाह रहे flow कैसा है. You want to visualize how the flow is taking place. See, I told you again, fluid is slightly difficult to visualize. Fluid flow is difficult to visualize. Imagine I'm throwing a pen. If I throw a pen, you can visualize the pen moving because pen is a single body. But imagine fluid flowing. Fluid, I told you previously also, don't imagine fluid as a single body. Fluid is a sequence of infinite bodies which are interconnected to each other, which are randomly moving. So therefore their visualization becomes difficult. Since their visualization becomes difficult, you are going to have multiple modes of visualization, multiple ideas of visualization. The first one and the most important one happens to be an imaginary pattern called a streamline. Imaginary has streamline. Streamline. After streamline, we are going to discuss something known as path lines. After path lines, you're going to discuss something known as streak lines. All these are ways of imagining flow, how the flow is doing. Finally, you're having timelines. Timelines. Easiest part in the entire subject, in the entire fluid kinematic subject is this particular part, easy part. Okay. Now come to the last part. This part will be slightly difficult for you, but don't worry. In examination, simple questions are coming from here. Otherwise, this is very difficult part. The third part is very difficult, but simple questions are coming. What is this? Imagine you are having a fluid element. Imagine Kiji, this is a fluid element. Okay, very big fluid element. Let us say you are having some fluid element over here. This, let us say, the fluid element. Now, this fluid element, when it is moving in a particular flow, it has to deform, because fluid element is not a rigid body, right? It is going to deform. Since it is going to deform, we want to understand how the deformation takes place. So over here, we will discuss the concept of deformation. Now you go and ask anyone, okay, who knows some engineering, how many types of standard deformations are there? He will say there is elongation, contraction possible, which is known as linear deformation. And there is one more deformation possible, which is angular deformation, which is having a more refined term called as shear deformation. तो पहले आप पढ़ेंगे deformation, जिसमें linear and shear deformation both you are going to see. Apart from this, when this fluid element is moving in a particular flow, it can even rotate while flowing. When it can rotate while flowing, you are going to have something known as rotation. You'll have something known as rotation. Under rotation, you will see some more concepts known as vorticity. And you will see something known as circulation. Vorticity भी देखेंगे आप, circulation भी देखेंगे आप. Finally, you will be coming to the last concept. Those are functions. There are two types of functions defined. Mathematical concept है बहुत. One is known as stream function. Stream function. Other is known as potential function. Potential function. This is known as organizing a particular subject. Why is this important? This is how, whenever you start studying for competitive examinations, I'm telling you, I was never a very good student in university examinations and all. Okay, without studying much, I could manage good marks. Okay, but competitive examinations I understood well. The reason is competitive examinations require more aptitude, more logic, and less effort sometimes. If you are able to organize the subject, आप subject कैसे develop पूरा समझ सकते हैं. What is leading to what? What is leading to what? If you can do, remembering all these things will be very easy for you. Are you following? This topic I'm going to take for some 9 hours, 10 hours. I won't see anywhere. I'm able to say the reason is only because I know how the subject is proceeding forward. You should learn the same thing. Try to understand how the subject is proceeding forward. Any subject, पहले create कर लो कि क्या क्या है. What is the sequence of events? ठीक है? You can take a snapshot, then we'll start this chapter. Take a snapshot quickly. Someone wanted this particular slide. Please take this quickly. Chaliye, moving further. Now I'm going to start with the approaches to the subject of fluid kinematics. Why do we require multiple approaches? As such, in mechanics also you're having both approaches, Lagrangian and Eulerian. But in fluid kinematics, its importance all the more increases. Why is it so? You see, when you're having, imagine you're standing on top of a building and you're looking down into a traffic. Okay, you're looking at a traffic You're observing only in the entire road, let us say there's only one vehicle moving. Only one vehicle is there that is moving. If I ask you to imagine its motion or visualize its motion, you will say it is very easy. But imagine there are some hundreds of vehicles randomly moving. Now I ask you to say how the flow is or how the motion is. You will say it is difficult to imagine. It is difficult to analyze. Since it is difficult to analyze, now what we will do, we will try to simplify by taking different approaches. Same thing is with fluid mechanics also. In fluid mechanics, you don't have a single body moving. You're having multiple particles, infinite particles randomly moving. For that purpose, we are defining approaches now. There are two approaches to the subject. Let me start over here. Approaches. There are two approaches to the subject of fluid kinematics. There are two approaches to the subject of fluid kinematics. The first approach is known as Lagrangian approach. Lagrangian approach. The second approach is known as Eulerian approach. Some people pronounce it as Eulerian, but the actual pronunciation is Eulerian. Okay? Name is Euler, not Euler. Dikta Euler, लेकिन है Euler. Lagrangian approach and Eulerian approach. These are the two approaches we are having. Let us start with the first approach. First one, Lagrangian approach. Okay. अब आप सोचिए, you try to imagine you are standing on top of building, very big building. Down there is some traffic flow, and you are visualizing the flow. Okay. I tell you now. Okay, whatever I'm telling you, आप देख रहे हो उसको. Try imagining. Okay. I tell you now that instead of looking at all the vehicles, concentrate on the motion of only a single vehicle. Concentrate on the motion of only a single vehicle. This kind of approach of visualizing the flow is known as Lagrangian approach. So what is Lagrangian approach? The study of fluid kinematics. The study of fluid kinematics. Fluid kinematics in which a particular particle is chosen in a flow field. Is chosen in a flow field. You are choosing a particular particle, comma. Its kinematic behavior is analyzed. Field and its kinematic behavior is analyzed. This particular approach is known as Lagrangian approach, where you are going to choose a particular particle and you're going to observe how the motion of that particular particle is taking place. That is known as Lagrangian approach. It is known as Lagrangian approach. I hope you are following this thing. Now, in Lagrangian approach, imagine you're having some flow field like this. There is some flow field. Whenever I draw this particular box, imagine there is flow taking place in this particular field. In this flow field, let us say you have chosen a particular particle. There is a particle you have chosen, some particle you are choosing, and you're observing how it is moving. Let us say this particle is moving from here. It is going like this. It is going like this. So suppose it has come over here. Someone is asking what is the meaning of kinematic behavior. Kinematic behavior means what is the velocity of the particle at various instants, what is the acceleration, how much displacement it is observing. All these things are kinematic behaviors you're analyzing. So imagine that this particle was having some initial velocity over here, v naught. At time t equal to 0, particle was over here. At some random time t, particle is over here. Let us say it is having some velocity v over here. Now this velocity v has to be a function of initial velocity and time. This velocity v has to be a function of initial velocity and time. Similarly, let us say the particle is having some acceleration over here. Initially, it was having some acceleration a naught. Okay, the value of a will be equal to a function of a naught and time. So we can say a general equation for Lagrangian approach is represented by what? It is represented by parameter of a particle. Let us say S is representing parameter of a particle, has to be a function of initial parameter and time. So let us say S over here stands for parameter. S naught over here stands for initial parameter. And T stands for time. For example, in basic mechanics, you might have studied an equation like this. An equation which says V is equal to U plus AT. Look at this particular equation, V is equal to U plus AT. What do you have in this equation over here? In this equation, you can see that V is some parameter. It is depending on what? It is depending on U, which is initial parameter, and time. This is something like Lagrangian approach only. Are you following this thing? So whatever equations you have studied in your basic mechanics, they are actually equations based on Lagrangian approach, where you are going to choose a particular particle in a flow field and you are going to analyze how it is moving in a particular flow. It's kinematic equations you are going to define. That is Lagrangian approach. One more thing. The path observed by the particle, in the flow is known as. So you see the particle started from here at time t equal to 0. It kept on moving. It is going over here. It is traveling some particular path. This particular path is known as path line. Details of this path line will come again later on. You see over here, path lines I have mentioned in the previous slide. Details of path line, definition, properties, all those things we'll be discussing later on. Right now, I am just telling you that in Lagrangian approach, you're having a particular visualization pattern known as path line. Okay, this is the first approach we are having. Take a snapshot if you want. Now come to the second approach. Second approach is more important for us. This approach, second one, is known as Eulerian approach. Now what happens in Eulerian approach? What do we do in Eulerian approach? Listen to this thing. The study of fluid kinematics. In which a suitable frame of reference, is chosen in a flow field. First thing, you are going to choose a suitable frame of reference in a flow field. After this, what are you going to do? After this, every parameter, by parameters we mean both kinematic as well as hydrodynamic parameter, is defined is defined for, this is important, positions as a continuous function of, as a continuous function of space and time. Space and time. The study of fluid kinematics in which a suitable frame of reference is chosen in a flow field and every parameter is defined as a continuous function for positions as a continuous function of space and time. This will be slightly difficult to understand. Please bear with me, be patient, I'll explain to you. Okay. You see, in Eulerian approach, what we do is we say particles are not important. Particles are not important. We say that, recall, there's a particular concept known as continuum. Continuum concept is there in our subject. What is this continuum concept in our subject? In short, we have discussed already continuum. In short, continuum is saying that if I'm having a particular flow field, let us say I'm having some flow field over here. In this flow field, at every space location, every time instant, there should be a particle. Hold this thought now. Again, I'm repeating and try to remember this thought now. Continuum बोल रहा, क्या बोल रहा continuum? It is saying that in this flow field, every time, at every space, there is some particle, fluid particle available. Fluid particle is available. Now what we do, if every position is going to have a particle, forget about particle. Let us say we define parameters now for position. For example, I am choosing a frame of reference over here. Let us say the frame of reference I'm choosing. The frame of reference I'm choosing over here is x-axis, y-axis, and let us say some z-axis. Then I'm saying this particular position, this is a position now. This particular position is having a velocity. And the velocity over here is a function of what? It should be a function of space and time. That means space matlab x, y, z, time matlab time t. Okay. Space coordinates are global coordinates, time coordinate is local coordinate. So your velocity over here is a function of x, y, and time. Whose velocity is it? It is not particle's velocity. Particle ka concept ho gaya. Lagrangian discussed particle. This velocity v over here, it is a velocity for position defined. Now you can ask me, sir, how can a position have a velocity? How is it possible for a position to have a velocity? For example, if I say the corner of a road, the velocity is equal to 10 km per hour in this particular arc. Does it mean that this corner of a road is standing up and moving in an arc? No. The meaning over here is any vehicle coming over here will take this much of velocity. So the meaning of Eulerian approach is, instead of attributing the parameters, instead of giving the parameters to particles, give it to positions. Particle will come over there, take that particular value. Are you following this thing now? Are you all following this thing? No. First answer is no only. See this. You are supposed to. अच्छा ऊपर से जाना सब. Very good. I appreciate your honesty. When we are separated by this much of distance, you can afford to be very honest, right? In class, people are not this much honest. In physical classroom, people are not this much honest. समझ में नहीं आ रहा तभी आ रहा बोलते. But when you sit in a different city, I sit in a different city, you can afford to be very honest now. See, Eulerian approach basically means, समझ में नहीं आया तो I have a different way of explaining. This I call as a slang way of explaining. Best way of explaining is what I discussed just now. Okay. If you did not understand this way, you understand like this. Highway. This is highway. You see over here 80. What is the meaning of this 80? You see a stand now, 80. What is the meaning of 80 over here? What is the meaning of 80? Yes. 80 over here basically means that allowed speed, is it not? Speed limit, very good. Speed, design speed, okay. I don't know all those terms. It is something like speed that is allowed. 80 से ज़्यादा गए तो पुलिस वाला आता, right? Now, if you see 80 over here, let us say some policeman standing over here is saying this position A. He is not an engineer. Policeman is not an engineer. This position A is having a velocity of 80. Means what? He's saying that this position A is supposed to allow any particle coming with a velocity of 80. When I mentioned 80 over here, I mentioned for a position, but it does not mean position is standing up and moving somewhere. It basically means, let us say this is your car. Your car comes over here, it will take 80 km/h velocity and move forward. Behind your car, some other car is coming. Some other car is coming, it is coming over here, takes 80 and move forward. This kind of approach where you are giving the parameters to positions instead of particles is known as Eulerian approach. Why is this approach suitable in our subject? Why is this approach suitable in our subject? The reason why this approach is going to be suitable for us is this word over here, continuum. You see, when there is particle available everywhere over here, everywhere you are having particles available over here, then you can say that at every position particle is available. So instead of particle, talk about positions now. When I say this position is having so and so velocity, it means the particle coming over here will take the. When I say this position is having so and so acceleration, it means the particle coming over here will take that particular acceleration. This is known as Eulerian approach. Lagrangian approach was particle oriented approach. Eulerian approach is position oriented approach. Eulerian approach is position oriented approach. Okay, this is position oriented approach. Now, what is the general equation? General equation in this particular approach. In this particular approach, the general equation is the parameter over here has to be a function of space and time. The parameter has to be a function of space and time. Now this parameter is what? This parameter over here, it is the parameter of position. Parameter of position. Parameter of position can vary with respect to space as well as with respect to time. This is the concept of Eulerian approach. Now, which approach we are going to find most commonly? Remember, more than 80% of the time we are going to find Eulerian approach in our subject. Very, very rarely we are going to find Lagrangian approach. Lagrangian approach we are going to see very rarely. Okay, I'll do one thing. I am sensing that you people are having a lot of difficulty for all these things. Anyway, starting the next concept also, there's no point, because if I start velocity, I have to discuss classification immediately. That much time is also not there. I will stop now. You tell me, bouncers जा रहे अरे यार. देखिए, it is not. I'll take 1 minute to just tell you. Thank you, Shiva Manjit. Thank you. That's very, very kind of you. See, what is space, sir? Nice, nice. I'm liking your questions now. Okay. Okay, officially class is finished. Okay, you can move out. अब मैं unofficially in the sense एक casual तरीके से discuss करेंगे Okay, what exactly is, let us right now, okay, you don't comment please, okay, you casual बोलते ही comments आ जा रहे हैं फिर से, ठीक है. Okay, wait on. Now, thank you, Sanket, very kind of you. Now listen, see, look like this. Try to imagine that you are inventing something. Please stop commenting, please, okay, please stop commenting. Let us discuss something. This is something which is very close to me. This concept actually. Imagine how people, thought of new ideas in mathematics. How did the new ideas come in mathematics? For example, when I say some parameter u, I'll take only 5 minutes. Okay, wait on. A parameter u is a function of x and y, for example. Let us say this first mathematician to have seen this kind of equation. And that mathematician got an idea. Okay, bhai, you have to find out a small change. Then what did that mathematician do? I showed you some time back. He said that, let me first of all go along x-axis. So this, what he's doing over here is, he's fixing something. What did he fix initially? He fixed y, and he was observing variation with respect to x. This is what he did first. Okay. Then he fixed x and observing the variation with respect to y. This might be looking very trivial to you. This might be looking very silly to you or small to you. No. This is actually a philosophy in itself. ये एक philosophy है. And this philosophy is useful in your day-to-day life also. Whenever you are having a problem which is complicated, then what do? You break it down. This philosophy has given birth to a complete subject by the name finite element analysis. You see, in finite element analysis also, you are not going to observe the entire problem as it is. You will break it down. So this philosophy is what is used in our subject also. In our subject, imagine that in a particular flow field, there are some parameters randomly moving. Many particles are moving. Imagine कि someone is throwing a ball towards you and asking you to catch. आप आराम से पकड़ लोगे. All of us know how to catch a ball. Fine. But imagine there are 100 people throwing 100 balls at you immediately and asking you to catch. अब क्या बोलोगे आप? नहीं. I have to fix something. What should I fix now? Let me concentrate on only one ball. If I concentrate on all the balls, it is impossible. It is impossible for me. If I concentrate on all the balls, it is impossible. So क्या possible है वैसे? Let me concentrate on one ball. If I concentrate on one ball, that is your Lagrangian approach. आप फिक्स कर रहे हैं क्योंकि आपका प्रॉब्लम कॉम्प्लेक्स हो गया, आप अब कुछ फिक्स कर रहे हैं, ये Lagrangian approach हो गया. Next, imagine now when these 100 balls are coming towards you, what you are doing right now is, instead of concentrating on ball, let us say your hand is in a particular position. Your hand is in this particular position. You are saying, for me, my position is fixed. My position is fixed. जो भी ball यहाँ पे आता, I'll catch it. मेरे को particle से मतलब नहीं. I don't care about particle. जो भी ball यहाँ पे आता, I'll catch it. Are you following this thing? That approach where you are having position important for you instead of particle, that approach is Eulerian approach. I hope. Okay, I can't say beyond this now. I'm also slightly tired. Okay. Chaliye, now let us speak. You raise your hands up. चलिए, Bikash Prasad.
Hello sir, good morning.
Morning sir.
सर वो एक आपने जो हाइड्रोस्टैटिक पढ़ा था उसमें आई लेने में प्रॉब्लम हो रहा था सर.
किसमें प्रॉब्लम होता? आई लेने में प्रॉब्लम होता?
जी सर. एच स्टार में एच बार प्लस आई साइन स्क्वायर थीटा अपॉन एच बार ए, वो उसमें आई का प्रॉब्लम हो रहा था सर. आई कैसे ले?
आई कैसे लेना है?
जी.
a case, let us take a particular case. Imagine you're having a particular fluid over here, you're having a particular plate over here. Okay,
Yes.
आप फ्रंट व्यू, ये आपका फ्रंट व्यू है, मान लीजिए सर आप देख रहे हैं ये आपका फ्रंट व्यू। अब क्या करेंगे आप, ओके, यू आर गोइंग टू क्रिएट अ प्लान व्यू। प्लान समझते हैं आप?
जी सर, ये अभी टॉप व्यू दिख जाएगा शायद।
टॉप व्यू नहीं, टॉप व्यू नहीं बोल रहा हूँ मैं, आप यहाँ से देख रहे हो। नाउ यू
हाँ 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 सर।
surface. So this is visualized perpendicular to surface. अब आपकी आंख यहाँ पे है, आपकी आंख यहाँ पे, यहाँ से देख रहे हो surface, ठीक है। I'll just tell you one thing, उसको याद रख लो, उसी तरह से करो। Okay, then this over here is your x-axis. Take y-axis, that's it. Take
Okay.
y-axis. So imagine it is a rectangle. Imagine ये rectangle है, ये rectangle है। Okay, अब मैं डायग्राम ड्रॉ नहीं कर रहा हूँ, ये मान लीजिए ये रेक्टेंगल है, ये 4 मीटर, ये 3 मीटर्स है। अब बोलो आई कितना है यहाँ पे?
वो तो सर ये आई आपका फिर ये जो भी होगा वो 3 के क्यू होगा सर।
नहीं कैसे?
4 into 3 का क्यू by 12 ऐसा।
नहीं, आपको आई का फिजिकल मतलब अभी समझ में नहीं आया। आई का देखिए, इस एक्सिस के अबाउट आप उस बॉडी को रोटेट कर रहे हो, तो ये आपके लिवर आर्म।
ओके सर, ओके
ठीक है ना, ये आपका लिवर आर्म हो गया। इसको अब क्यूब मिलेगा, सो क्या आ जाएगा अब यहाँ पे आपको?
3 into 4 of क्यू by।
ठीक है ना सर?
ओके सर,
चलिए
समझा सर।
ओके, थैंक यू। ऋषि आनंद।
हेलो सर।
हेलो सर, मॉर्निंग
सर एक्सीलरेशन वाले स्लाइड पे गए ना सर, वहाँ डिफरेंस नहीं समझा, मुझे एक बार बताइए।
देखो यार, वो सब तो मतलब मैं दिखा तो दूंगा
सर, मैथमेटिकल नहीं समझा, बाकी ये समझो।
आप किस डिपार्टमेंट से हैं?
सिविल सर।
सर सिविल से है ना, तो इतना ज्यादा जरूरी नहीं है, मतलब डोंट गेट मी रॉन्ग, आई एम जस्ट सेइंग कि इफ दिस इज स्ट्रेसिंग यू आउट, दिस मच इज जस्ट अंडरस्टैंडिंग द मीनिंग इज सफिशिएंट। मतलब आपको कम से कम ये समझ में आ रहा?
हाँ सर, ये समझ में आ रहा।
इतना समझ जाओ, इट इज सफिशिएंट। देखो, अगर आपको डेरिवेशन चाहिए, कैसे क्या बन रहा, फिजिकल मीनिंग चाहिए, आई कैन एक्सप्लेन, but that will be slightly difficult for you also. It's up to you, then let me know. Do you want to understand the physical meaning and all?
सर मुझे ये ऊपर का है ना, वो आपने किया, वो नहीं समझा।
ये समझ में नहीं आया आपको?
हाँ।
देखिए, then you see, any vector, हर वेक्टर के दो कंपोनेंट्स होते हैं, एक उसका मैग्नीट्यूड है और एक उसका डायरेक्शन है। ठीक है, मैग्नीट्यूड को हम मॉड से रिप्रेजेंट करते हैं, डायरेक्शन को कैप से रिप्रेजेंट करते हैं। अच्छा, आप जब किसी चीज को यूवी को डिफरेंशिएट करते हैं, यूवी रूल पढ़े होंगे आप कि u डैश v प्लस v डैश u, पढ़े?
यस सर।
डिफरेंशिएशन, तो डिफरेंशिएशन ऑफ uv इज इक्वल टू समथिंग लाइक दिस। वही कर रहा हूं मैं यहाँ पे, v mod v into dv cap by dt एंड v cap into d mod v by dt कर रहा हूँ। इस केस में क्या हो रहा है? यू आर लुकिंग फॉर चेंज इन डायरेक्शन ऑफ वेलोसिटी। इस केस में क्या हो रहा है? चेंज इन मैग्नीट्यूड ऑफ वेलोसिटी देखा जाए। ठीक है ना, इतना ही समझ जाओ, काफी है।
समझ गया सर, समझ गया।
ठीक है, थैंक यू। एनीवन हैविंग डाउट्स प्लीज रेज हैंड। वन हैज अ डाउट? Suklesh Satyam Setti.
Hello sir.
Hello sir, good morning.
Good morning sir. Sir, I have a doubt. Just give me 1 second sir, I'll search the question.
Sure.
1 second. Hello sir.
हाँ sir, tell me sir. Tell me sir.
Yes sir, 1 second. Sir, first I want to know that there is one beaker sir.
There is one? Can you be loud please?
There is one beaker.
Okay.
So it is filled with water till a height h, small h. Okay sir. So in that we have placed an ice cube.
Okay.
Inside that ice cube there is a some small paint.
Okay.
The density of paint is greater than the density of water.
Okay.
So now, sir, what will happen to the level of water
Hmm.
inside the beaker when the ice melts?
What will happen to the level of water
When the ice melts,
when the ice
melt.
melts?
Yeah, sir. I want to firstly know what.
One second. Let me first of all imagine the entire situation.
Acha, okay, sir.
So this is inside there is something which is having specific gravity greater than 1.
Yes, sir.
ठीक है.
And that outer portion is ice.
Ice. This is ice. S less than 1 है ये. S equal to 1 है. Basically story is something like this. S less than 1 है ये. Okay. Okay. Level of water will drop down.
सर कैसे सर?
Correct
मतलब
answer.
imagine कैसे करना है इसको?
Correct answer.
Sir, actually I don't know the answer. I have to check out. This is forwarded by my friend, one of my friend.
If S is over here greater than 1, level of water should drop down. How?
Yes, sir. Yes, sir. Okay.
First of all, did you understand this kind of problem where you are having ice S less than 1, S equal to 1, melt hota, level of water will remain same.
No, sir. That one also I didn't get. I
I
want to know.
discussed this thing yesterday, na? I'll do one thing. I'll explain you this thing. Then you
Acha.
think over this particular case.
Yeah, yeah. Okay.
Okay, na?
Okay, sir.
Now, what is happening in this particular case? Whatever is the value of weight of ice has to be equal to FB, correct?
Yes, sir.
Weight of ice means gamma of ice multiplied to volume of ice. This has to be equal to FB. FB means gamma of water in
Water into
volume of water,
displaced. Yeah. Yes.
displaced water.
Yes, sir.
अब देखिए, when ice is melting, then the value of gamma of ice is becoming equal to gamma of water.
Okay.
मतलब क्या है, जब ice melt हो रहा है उसका density बढ़ रहा है, its density is increasing.
Increasing. Yes, sir.
And it's, see, if
The volume is
its
decreasing.
volume should decrease and become
Yeah.
exactly equal to this value. That means जितना shaded portion है उतना ही exact volume बनेगा यहाँ पे.
अच्छा 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 अच्छा.
Are you following this thing?
Yes, sir. Yes, sir.
Exact
Yes.
volume बनेगा. इसीलिए क्या है, जितना भी ice melt हो जाएगा वो इतने volume में पानी बन के बैठ जाएगा.
Okay.
Okay ना?
Okay, sir.
This is the concept right now we are having. Up now we have to think over here. Gamma of ice multiplied to volume of ice plus gamma of paint multiplied to volume of paint is equal to gamma of water multiplied to volume of water.
Water. Okay. Okay.
ठीक है?
अच्छा.
Now
अच्छा.
he is melting and becoming gamma of water. He is melting, becoming gamma of water. वो थोड़ा कम गामा, इसको न्यूमेरिकल से अच्छा इसको लॉजिकली कर सकते हैं आप.
या ये लॉजिकली है सर, मतलब इसमें न्यूमेरिकल तो नहीं दिया है.
न्यूमेरिकल करने का नहीं है, इसको लॉजिकली कर सकते हैं आप कि अगर इस जगह पे आइस होता, पेंट की जगह पे भी आइस होता तो इतना ही पानी बनता हो.
यस सर.
ही पानी बनता हो. अब ओके ओके ओके, वन सेकेंड, एक मिनट. हाँ,
यस सर.
आएगा. Again, it is supposed to remain same only, I believe.
So whether it is its density is greater than or less than, it should remain same. How?
एक सेकंड, 1 second. Imagine ये पेंट है मान लो. अरे 1 second, ये आइस है मान लो. दिस इज आइस. This much of ice will melt. क्या क्वेश्चन है ये? This much of ice will melt
सर हम ऐसा सोच सकते हैं क्या सर कि
बोलो।
वॉल्यूम ऑफ आइस में थोड़ा सा वॉल्यूम तो वो नील पेंट ऑक्यूपाई कर रहा है वैसा।
हम्म। वही कर रहा हूँ, ये पूरा आइस है, बिगर सर्कल इज आइस,
तो
स्मॉल।
सर वहाँ पे वॉल्यूम ऑफ आइस में फुल्ली वो वॉल्यूम ऑफ वाटर नहीं होगा ना, वो थोड़ा सा कम होगा जितना ये वॉल्यूम ऑफ पेंट का। जैसा पहले वाला केस में सर वॉल्यूम ऑफ आइस फुल्ली वॉल्यूम ऑफ वाटर हो जाएंगे, अभी इसमें थोड़ा सा बच जाएगा क्योंकि वो वॉल्यूम ऑफ पेंट में है।
हाँ, this paint over here. It is going to remain as it is. Right. Answer comes down. Look over here. Excuse me, are you able to listen?
यस सर यस सर।
हाँ, इमेजिन कीजिए कि this entire portion was ice. Then
ओके
it will come down exactly to this level, correct?
यस सर।
Okay. Now you imagine that this entire portion is not ice. एक काम करते हैं, इसको ऐसे ले लेते हैं. Let us take it like this to understand better. Okay. Some nail paint over here, for example.
ओके ओके
Okay, it is going to be over here only.
यस सर।
Comes down भी नहीं होता आंसर फिर.
सर
नहीं, remain same रहेगा यार. I'm sorry. I'm really sorry. It should be remain same. देखिए. Let us say this is ice. This is that nail paint.
यस सर।
Nail paint will be remaining over there only. मान लो ये यहीं पे रहेगा.
ओके
ये यहीं पे रहेगा. जब ये मेल्ट हो जाएगा तो इतना ही बन जाएगा वो.
ओके, तो
Ice.
ये नेल पेंट वैसे ही रह जाएंगे।
Nail paint will settle down over here. But वो तो पहले से ही पानी के अंदर है.
अच्छा, तो जब सेटल हो जाएगा तब वाटर लेवल रेज तो नहीं होगा ना?
नहीं, रेज नहीं होगा. पहले ही पानी के अंदर है ना वो.
ओके ओके ओके।
पहले ही पानी के अंदर है. It will remain same only. It will remain same only over here.
ये पहले पानी के अंदर है इसीलिए, अगर वो नील पेंट उस ऊपर वाले पोर्शन में होता शायद तब उस टाइम रेज हो सकता है ना सर?
अब देखिए, ऊपर वाले पोर्शन में होता.
अगर होता
नहीं, तभी नहीं, तभी it will not be affected.
क्यों सर, तब तो होना चाहिए था ना, क्योंकि अभी इसमें है इसीलिए ऑलरेडी वो फ्लूइड डिस्प्लेस किया हुआ है तो इसीलिए वाटर लेवल रेज नहीं होगा।
नहीं, तब वो थोड़ा इसको क्या आइस को और थोड़ा नीचे पुश कर देगा ना.
अच्छा, वो पहले ही पुश करके
अब मान लीजिए,
चले।
अब इस आइस को और थोड़ा नीचे आप पुश कर रहे, तो पहले ही मतलब जो पानी का लेवल रह गया वही लेवल पे रहेगा ना. अगर नेल पेंट ऊपर था तभी वो आइस को थोड़ा पुश कर देता नीचे.
पर ये मेल्ट होने के बाद, अच्छा ये तो आएगा ना सर वाटर के कांटेक्ट?
हाँ, सी, वॉट कंडीशन ऊपर रखने से होगा, सेम कंडीशन नीचे रखने से भी होना चाहिए. दो डिफरेंट कंडीशन नहीं हो सकते यहाँ पे.
अच्छा, क्योंकि
हाँ.
मेरा डाउट है कि इसमें तो अगर फ्लूइड डिस्प्लेस करने का ये कॉन्सेप्ट है तो ये ऑलरेडी फ्लूइड के अंदर है तो इसलिए हम ऐसा ले रहे हैं, पर ये तो फ्लूइड के अंदर नहीं है ना सर, डिस्प्लेस नहीं किया ना।
सर, अगर ऊपर भी होता तो इट इज गोइंग टू पुश दिस आइस डाउन ना.
विथ इट्स वेट।
दोनों एक कॉम्पोजिट बॉडी बन जाएंगे ना,
अच्छा
तभी इट इज गोइंग टू पुश आइस डाउन.
अच्छा अच्छा, ओके
ठीक है ना.
ओके सर, थैंक यू सर।
थैंक यू. नव्या.
Good morning, sir.
Good morning, ma'am.
There is a small doubt. I mean, it's not a doubt, but why do we choose? I mean, we not choose. Why do we use Eulerian method on top of Lagrangian method?
Why do we use Eulerian method over Lagrangian method? The reason
Huh.
is, you see, in Eulerian method, at a particular instant, you're getting the idea of every position. For example, if I write velocity is equal to some, let us say, x square plus some, let us say, x square minus x square I minus 2xyj, for example, 2D flow, let us say. I'm writing this thing. So I am getting the idea. I'm getting the idea for every position's velocity at a single instant. Are you following? Let us say
Yes,
this
sir.
is something, this position is something. At every position, if I put over here, I will get the idea of velocity for every position over here in Eulerian approach. But the problem with Lagrangian approach is when you're concentrating only on a particular particle, then you have to have a different observer for another particle. You have to have a different observer for another particle. Likewise, you'll have to have multiple observers for Lagrangian approach. In Eulerian, that is not required.
Okay, that means we in the Eulerian method, we write equation with respect to position. I mean, yeah, with
Not with
respect to
respect to for. Let us say for positions.
okay, for positions.
Hmm.
So it is only one equation to define the position. I mean positions.
No, you can.
I'm not able to visualize the equation actually, the general equation. That is my problem.
This, you're not able to visualize this equation.
You wrote nas parameter. I mean
As
parameter of
the
position is
function
equal
of
to
space and
function of
time.
space and time.
Okay. This I'll explain you how to visualize, but that is okay. You listen now. What is the meaning of variation over here? Look over here. Imagine you are having a very big flow field. This is some
Okay,
big
sir.
flow field, let us say. Okay, let me do one thing. For flow field, let me show XY axis. Suppose this is a flow field, let us say. This is some Y axis. This is some X axis. Now in this flow field, let us say you have taken a subject volume. This is called as control volume also. You have taken a subject volume. Subject volume, for example, this is control volume, subject volume. This length, let us say, is equal to dx. This length, let us say, is equal to dy. This length, let us say, is equal to dz. Okay.
Yes, sir.
Let us take a particular particle over here. This particle is A. This particle is A. Over here, the velocity is equal to 3. The velocity over here is equal to 4. The velocity over here is equal to 5. Velocity over here is equal to 5.
Yes, sir.
Let us say I go forward to this position. Let us say this position's name is B position. My velocity over here is equal to 4. Now this velocity is u velocity, x-axis velocity. This velocity is again x-axis velocity, u velocity. I'm saying u is equal to 3 over here. I'm saying u is equal to 4 over here. What does it mean? The value u is
with respect to
what?
position.
Space. That which space axis? X. So over
X.
here I'm finding u over here is a function of what? X.
X.
Let us say over here, the value of u is again equal to 3. Tell me, as I move in y, is the value of u changing over here?
No, sir.
It is not
It
a
is
function.
constant. It is
It
not the
function
function of y.
It is not a constant. Let us say it is not a function of
Y.
Let us say over here the value of u is equal to some 6. Now which axis you are moving? Look at my
Z.
cursor. Z. That means it is a function of what?
Z. Okay.
Example I'm giving you, just an example. Let us say now you blink your eye. You blink your eye. Okay. You close your eye for a moment.
Yes, sir.
I'm writing 13 over here. Same position. I'm fixing the position. But next instant, I'm saying that there is a velocity. The position over here is having a different velocity. That means it is a function of what?
Time.
Perfect. Very good. Very good. It's a function of time. This is the meaning of any parameter being a function of space and time. Are you
Okay,
following?
sir. Got it. Yes, sir.
Space basically means, now listen to this carefully. I ended my class with a casual statement that whenever things become complex, try to simplify by fixing some things. Is it
Yes,
not?
sir.
Same concept over here. The meaning of space variation means you fix time, observe space. You see, when I talked about 3 to 4, then 3 to 6, 3 to 3, did I tell you that time is changing over there? No.
No.
That instant only different position having different thing. Then what about this time thing? What did I fix over here? You see, I said 3 over here. I said 13 over here. What did I fix over here?
Space, position.
Ah, perfect. I fixed space. And then I was observing change with respect to what? Time.
Time.
This is
Okay.
the meaning. Okay. See, the problem, this particular subject is kinematics chapter. It becomes clear when you see it multiple times, you practice it multiple times, then this becomes clear. When I was studying, for me also, this much clarity was not there. When I started teaching, that time also lesser clarity only than what I have. After these many years of teaching, we get this much of clarity. So
Okay.
this chapter is basically visualization of calculus. Problem is, when generally we study calculus, we do not study calculus from the point of view of application of calculus. We say that if y is equal to 3x, dy by dx is equal to 3. Meaning kya hai, we don't know. But we study calculus that way. Is it not? Generally, I'm saying. Okay.
Yes, sir.
This is going to help you visualize the meaning of calculus over here. Probably when you studied what do you call partial derivatives, you were not knowing how much important partial derivatives can be. Now you will see what is the meaning of partial derivatives. So you have to practice more so as to visualize. But again, for examination, all this much detail is not required. What I have shown over here, that much detail is not required for examination. For examination, just for writing 2 steps, you'll get 2 marks. Those kind of questions are coming from kinematics. Because if they start asking you difficult questions from kinematics, you will spend half an hour, still won't get answer. Those kind of difficult questions are also possible. ठीक है ना?
Yes, sir. And sir, a silly doubt. It is of mathematics. The delta you mentioned and the delta, the triangle one, both are same.
D and delta. This thing
Yeah.
is
No. Delta. The
this one.
S-type delta. Yeah.
Okay, this is called as del. I call it as del, and this is delta. Okay.
Okay. Del and delta. Yeah.
This is small delta. This is capital delta. This is an infinitesimally small change. This is called as infinitesimally small change. This is a substantial change. Right. Okay. This is
So what is the
infinitesimally small.
physical meaning?
Physical meaning.
If you can explain.
Curve.
Yeah.
At a particular point, the small change over here, that is dy by dx. Basically, if I slope over here, the slope is going to be dy by dx. If I say a substantial value over here, let us say this is delta y, this is delta x. So I'm taking a substantial change,
Considerable
relatively
change.
big, considerable, correct word, considerable. That is delta. Fine.
Okay.
Is it
Got
fine?
it. Yes,
Thank
sir.
you.
Thank you, sir. That's it.
Harishri Arun.
Hello, good morning, sir.
Morning, ma'am.
Sir, I was confused with that space, the general equation of space with respect to time.
One second. Which slide are you talking about?
Last slide, sir, your O'Leary approach.
This one.
Yeah, yes, sir.
Tell me, ma'am, what is the difficulty in this?
So we took in a Lagrangian approach, we took no initial parameter as S naught, sir. But here we took space with respect to time, but space and time will be changing simultaneously, no, sir? How can you fix time?
Fixed time means at an instant you see every position. See, fixed time means, acha, how to fix time means, let us say you are watching some movie, you pause the video. Let us say
Okay.
you are watching some movie, this is a
Yeah.
you pause. Someone over here is doing something, someone over here is doing something, someone is doing something. Like that. Now what did you do? You fixed time. Time over here is equal to, let us say, third a second. You pause the video. Now you tell his velocity is this much now. His velocity is this much now. His velocity is this. This is called as fixing time. You pause a video. What do you mean by fixing space? You allow the video to move, but concentrate only on one corner of the video. You are fixing space now.
Oh.
Okay, na?
Okay.
Still, you'll be having doubts. I can sense that. You be patient actually till tomorrow's class. Once tomorrow class takes place,
Okay.
actually I prefer teaching kinematics within 1 or 2 days. Okay, but that requires around 10 hours. So that is not possible now. So because
But in Lagrangian approach, we are taking time. That is also we fix time, or we fix initial parameter.
over here, imagine you are supposed to observe only one particle. What is the point of fixing time? If you are only observing,
Okay. Yeah.
you don't need a fixing time.
Okay. Sir, and I am having a problem in that difference. In how to take that partial differentiate.
How to take means
solving. I'm not getting it.
If I take an equation, how to get that derivative of that? That is mathematics. Let us say 3y square t plus e power t, for example. Some equation I'm having. Okay. I want to get dou u by dou t is equal to how much? What do? You treat t as constant over here. You treat t as constant.
Okay.
Tell me one thing first of all. If I say 3y square, u is equal to 3y square, I ask you what is du by dy. What will you answer? Tell me at least the same. This is going to be
not getting to how to differentiate. I not able to get it.
This is equal to 6y. Are you not able to get this thing?
Yes, so that only.
No, you have to please go through mathematics because this is direct differentiation. If you are having difficulty with this, you do one thing. You go through standard formulas of differentiation. Standard formulas will be something like this. If y is equal to x power n, the value of dy by dx is equal to n into
nx.
This kind of formula. Some basic standard formulas you study. Okay. Then you come across this question. Don't worry, it's similar kind of question I'll be taking tomorrow.
Okay. Thank you.
Thank you. Vaishnavi.
Good morning, sir.
Morning, ma'am.
Sir, I had a doubt in the question where you explained about the melting of ice and the volume will remain same.
Tell me.
Sir, in that question, I can't imagine how is the volume remaining same and what about the part above the fluid?
See, you are having some container, you are having some ice. So, see, this ice has to become water now.
Yes, sir.
If ice becomes water, answer me this thing. If ice converts to water, will it acquire same volume, lesser volume, or more volume? Answer me this much first.
Lesser volume.
Lesser volume. So volume decreases. How much volume will it require? It will require volume exactly equal to, because you see, let us say gamma of ice. Gamma of ice is equal to some 8, for example. Example, say gamma of water is equal to, let us say, some 10. Okay. And volume of water displaced is equal to 8, let us say. Volume of ice initially is equal to 10. So we can say weight of ice is equal to weight of ice is equal to Fb. Initially we can say this much. Weight of ice is equal to Fb. So weight of ice means what? Gamma of ice multiplied to what? Volume of ice. Fb means what? Gamma of water multiplied to volume of water. Correct now?
Yes.
Now tell me, if the gamma of ice is converting into gamma of water. After melting, gamma of ice is converting into what? Gamma of
Gamma
water.
water.
That means the entire volume of ice should convert into how much ever volume of water was displaced initially.
Okay.
Correct? Huh? So basically this entire amount of ice is going to melt off and it will occupy only this much space. Because his density increases, he will experience contraction.
Okay.
His density is, tell me, his density is increasing or not? Look over here. Density
Yes,
of
yes. Density of water is greater than.
if ice to water density is increasing, so ice should experience contraction. And how much contraction? You see, if his density is becoming equal, his volume should become equal to the volume of water displaced. His volume will come down exactly become equal to this much volume only.
Okay, sir.
Okay, now?
So basically the relation will be like this only. Like.
See, the relation is gamma of ice is converting into gamma of water. Volume of ice is becoming equal to volume of water displaced. That's it. Nothing much to discuss about it. Clear?
Okay, sir. So then, like here, as you told, like it's basically interchanging, right? Like here, you have taken gamma of I equals to 8, and here the volume of water is equals to 8.
That example I gave you, madam. You.
Okay.
That is an
It
example.
is a proportion. Okay.
Yeah, it has to be in that proportion. For example, volume over here is equal to 16, then volume over here will be 20. I have to see to it that this product and this product should match. Okay, that's it.
Okay, sir. Okay, sir. I understood. Yes.
Okay, now.
Thank you, sir.
Thank you. Anyone else having doubts can ask.
Hello, sir.
Hello, sir. How Suklesh?
Sir, yes, in this yesterday's class, we have some like general translation, no, sir. General translation. So in that we will consider G effective tan theta is equals to x by G effective. Sir, in that we know the AX means the A cos alpha. But what is AZ, sir, here?
Yes, sir.
G plus AZ, no?
AZ over there is A sin alpha. अब देखिए, this is alpha, let us say, this is A. AX will be equal to A cos alpha. AZ will be equal to A sin alpha.
Acha.
Fit now. A sin alpha.
Okay, sir. Thank you, sir.
Thank you, sir. Anyone else is there? If no one else is there, I'm stopping the session.